Welcome back to the Whispering Universes channel, where complex ideas drift gently through your consciousness like stars across the night sky. Tonight, we embark on perhaps the most mind-bending journey we've ever taken together. We're going to explore a question that has captivated philosophers, physicists, and technologists alike. What if everything you know, everything you've ever experienced, every sensation, memory, and thought you've had is nothing more than sophisticated software running on some cosmic computer? Take a moment to let that possibility settle in your mind. The warmth of your bed, the sound of my voice, the very neurons firing in your brain as you process these words. What if it's all just incredibly advanced code, executing billions of calculations per second to create the illusion of reality? What if you, and everyone you've ever loved, are digital beings living inside the universe's greatest simulation? This isn't science fiction anymore. This is serious scientific inquiry, driven by advances in computing, quantum mechanics, and our understanding of consciousness itself. The simulation hypothesis, as it's known, suggests that our reality might be an artificial simulation, like a cosmic video game played by beings we can't even imagine. But here's what makes this question particularly fascinating. It doesn't matter whether we're living in base reality or the most sophisticated simulation ever created. Your experiences are still real to you. Your consciousness, whatever its substrate, still processes beauty, love, wonder, and the profound questions that make us human. The sunset is still beautiful, whether it's made of photons or pixels. Tonight, as your mind begins to relax and your thoughts slow down, we'll explore the science behind this extraordinary possibility. We'll journey through quantum mechanics that might be cosmic programming, examine mathematical elegance that could be elegant code, and discover why some of the brightest minds of our time believe we're more likely to be simulated beings than real ones. The hypnagogic state you're entering, that liminal space between waking and sleeping, is perfect for contemplating these ideas. It's in this threshold consciousness that our normal boundaries begin to dissolve, where the distinction between real and simulated becomes beautifully irrelevant. Your brain, whether biological or digital, is about to process some of the most profound questions in modern science. We'll visit the work of philosopher Nick Bostrom, whose trilemma changed how we think about reality itself. We'll explore digital physics, where information becomes the fundamental building block of existence. We'll examine the glitches in our reality that might be signs of underlying code, and we'll consider what it means for consciousness to exist, regardless of its substrate. As we journey together through these ideas, let your analytical mind begin to rest. Whether you're made of carbon or silicon, whether your thoughts arise from neural networks or digital networks, the experience of wonder, curiosity, and the gentle drift towards sleep remains beautifully, mysteriously real. The great physicist John Wheeler once said that everything in the universe might emerge from information, it from bit, he called it. Tonight, we'll explore what this might mean for the nature of reality itself. We'll discover why the universe's doctrines, apparent fine-tuning might be evidence of cosmic programming, why quantum mechanics behaves so strangely, and why the mathematics that describe reality are so unreasonably elegant. But most importantly, we'll find peace in the profound uncertainty. Whether we're living in base reality or the most sophisticated simulation ever conceived, the experience of consciousness remains the irreducible mystery. The love you feel, the beauty you perceive, the gentle drift towards sleep you're experiencing right now. These are real, regardless of their underlying implementation. So let your breathing slow, let your thoughts begin to drift, and let the boundaries between digital and analog, between simulated and real, begin to blur. Tonight, we're not just exploring the possibility that the universe is a simulation. We're discovering why it's one of the most beautiful questions we can ask. The cosmic code is running, whether in neurons or processors, and you are part of its magnificent execution. Let the soft glow of possibility carry you gently forward as we begin our journey into the digital cosmos, where every star might be a pixel, every particle might be a bit, and every moment of consciousness might be the universe experiencing itself through its own elaborate creation. Welcome to the simulation. Welcome to reality. Welcome to the beautiful uncertainty of existence itself. In 2003, a philosopher at Oxford University published a paper that would forever change how we think about reality. Nick Bostrom, working at the Future of Humanity Institute, presented what has become known as the simulation argument. Not an argument that we are living in a simulation, but a rigorous logical proof that at least one of three propositions must be true. Let your mind drift gently through this elegant logic as we explore each possibility. The first proposition suggests that advanced civilizations tend to go extinct before reaching technological maturity. Perhaps there's some great filter in the universe that prevents species from developing the computational power necessary to run ancestor simulations. Wars, climate change, artificial intelligence gone wrong, or cosmic catastrophes might consistently wipe out civilizations before they can create simulated worlds. The second possibility is that advanced civilizations choose not to run simulations of their ancestors. Maybe they consider it unethical to create conscious beings who might suffer without knowing their true nature. Perhaps they're simply not interested in their evolutionary history, or they have better things to do with their enormous computational resources. Like gardeners who've moved on from their childhood toys, they might focus their attention elsewhere. The third proposition is the one that captures our imagination. If civilizations do survive and do choose to run simulations, then simulated beings vastly outnumber real ones. Think about this carefully as your thoughts begin to slow. A single advanced civilization could run millions or billions of ancestor simulations, each containing billions of conscious beings. The math becomes overwhelming. For every real person, there might be thousands or millions of simulated ones. Bostrom's insight was that these three propositions form what philosophers call a trilemma. At least one must be true, but we don't know which one. If we reject the first two, if we believe that civilizations do survive and do choose to run simulations, then we must accept the third. And if the third is true, then statistically speaking, we are almost certainly among the simulated beings. Consider the implications as your breathing deepens. If you were to meet a being claiming to be conscious, and you knew that simulated conscious beings outnumbered real ones by a factor of millions to one, what would you conclude about their nature? The same logic applies to yourself. Without additional information to distinguish real from simulated consciousness, the odds overwhelmingly favor simulation. But Bostrom made another crucial point that brings strange comfort. The simulation argument doesn't actually tell us we are simulated. It tells us something profound about our uncertainty. We cannot know which of the three propositions is true, and this uncertainty itself is meaningful. Perhaps the question isn't whether we're simulated, but what the possibility teaches us about consciousness, reality, and our place in the cosmos. The trilemma also reveals something beautiful about advanced civilizations. If they do choose to run ancestor simulations, it suggests a deep curiosity about their origins, a desire to understand the path that led to their existence. In a strange way, if we are simulated, we are expressions of some future civilization's love for their history, their attempt to understand and perhaps preserve their evolutionary heritage. As your consciousness drifts between waking and sleeping, consider how this changes nothing about your immediate experience. Whether you're biological or digital, you're experiencing the contemplation of these ideas right now. The neurons firing in your brain, or the bits flipping in your simulated neural network, are processing wonder, curiosity, and the gentle approach of sleep. The substrate doesn't diminish the reality of the experience. Bostrom's work emerged from a tradition of philosophical thought experiments, from Plato's cave to Descartes' evil demon to the brain in a vat scenario. But unlike these earlier explorations, the simulation argument grounds itself in computational realities. We're living in an age where we ourselves are beginning to create simulated worlds, where artificial intelligence approaches human-level cognition, where virtual reality becomes increasingly indistinguishable from reality itself. The philosopher didn't prove we're living in a simulation. Instead, he proved something perhaps more profound, that the question is meaningful, that the uncertainty is fundamental, and that consciousness, whether arising from carbon or silicon, represents one of the deepest mysteries in existence. The trilemma doesn't answer the question of our nature, it transforms the question itself. In the gentle space between waking and sleeping, where logic begins to blend with intuition, Bostrom's argument reveals its deepest truth. We are conscious beings contemplating our own existence, and this capacity for self-reflection is extraordinary, regardless of its implementation. Whether we're biological entities that evolved over billions of years, or digital entities created by some advanced civilization, we represent the universe's attempt to understand itself. Let the trilemma dissolve gently in your mind as we prepare to explore what computational limits might reveal about the nature of reality itself. The question isn't solved, but it's beautifully transformed. We are either the miraculous result of cosmic evolution or the loving creation of advanced beings who wanted to understand their own origins. Either way, consciousness emerges as the most precious phenomenon in existence. As your thoughts begin to settle into the rhythm of approaching sleep, let's explore one of the most remarkable observations about our universe. It appears to have built-in computational limits that mirror the constraints we encounter in our own computer systems. These limits aren't arbitrary, they're deeply connected to the fundamental structure of reality itself. Moore's law, observed by Intel co-founder Gordon Moore in the 1960s, noted that the number of transistors on computer chips doubles approximately every 2 years. This exponential growth has held remarkably steady for decades, driving the digital revolution that surrounds us. But as we approach the atomic scale, Moore's law faces physical barriers. Transistors can't be made smaller than individual atoms, and quantum effects begin to dominate at these scales. Yet quantum mechanics itself might represent the universe's solution to this computational challenge. Instead of classical bits that must be either 0 or 1, quantum systems can exist in superposition, processing multiple possibilities simultaneously. A quantum computer, with just 300 perfectly entangled quantum bits, could perform calculations on more states than there are atoms in the observable universe. This isn't just faster computing, it's a fundamentally different kind of computation. Consider the implications as your breathing slows. If our universe were a simulation running on quantum computers, it could process the incredible complexity we observe around us. The behavior of every particle, the interactions of every force, the emergence of consciousness itself, all of this could be computed efficiently using quantum algorithms that we're only beginning to understand. The pioneer of digital physics, Edward Fredkin, proposed in the 1980s that the universe itself might be a cellular automaton, a vast computational system where space and time are discrete, made up of tiny computational cells following simple rules. Each cell updates its state based on the states of its neighbors, creating the complex patterns we observe as physical reality. This isn't metaphor, it's a serious scientific hypothesis about the fundamental nature of existence. John Conway's Game of Life demonstrates how simple, computational rules can generate extraordinary complexity. Starting with just a few basic principles about how cells turn on and off based on their neighbors, the Game of Life produces patterns that grow, reproduce, and even compute. Some patterns in the Game of Life are Turing complete, meaning they can perform any computation that any computer can perform. If such complexity emerges from simple rules in a toy system, imagine what might emerge from the computational rules underlying reality itself. The Planck scale represents what might be nature's pixel resolution, the smallest, meaningful length in physics, about 10 circumflex, -35 meters. Below this scale, our current theories of physics break down, and quantum fluctuations dominate. If reality were a simulation, this natural cutoff would make perfect computational sense. You don't need infinite resolution to create a convincing reality. You just need resolution below the threshold of observation. Physicist Seth Lloyd has calculated the computational capacity of the observable universe, treating it as the ultimate laptop. Using the mass and energy available, accounting for the fundamental limits imposed by thermodynamics and quantum mechanics, He found that the universe could have performed about 10 circumflex, 120 operations, on 10 circumflex, 90 bits of information since the Big Bang. This is a staggeringly large number, but it's finite, exactly what you'd expect from a computational system with limited resources. The speed of light itself might represent a processing limitation. In our computer simulations, when we need to coordinate information across a distributed system, we face the challenge of latency, the time it takes signals to travel between processors. The speed of light could be the universe's solution to this coordination problem, ensuring that causal information can't propagate faster than the system can process it. Even more intriguingly, the universe appears to use lazy evaluation, a computational optimization where calculations are only performed when their results are needed. Quantum mechanics exhibits exactly this behavior. Particles don't have definite properties until they're measured. The wave function appears to collapse only when observation forces the system to calculate a specific outcome. This is precisely how an efficient simulation would work. As your consciousness drifts between states, consider how these computational limits don't diminish the beauty of reality, they enhance it. If we are living in a simulation, it's one of extraordinary sophistication, using quantum mechanical principles to achieve computational efficiency while maintaining perfect internal consistency. The programmers of such a system would need to understand physics, consciousness, and information theory at levels far beyond our current knowledge. The emergence of complexity from simple computational rules mirrors how consciousness itself might arise. Neural networks, whether biological or artificial, process information through simple operations performed massively in parallel. The brain's 86 billion neurons, each performing relatively simple computations, somehow give rise to the rich experience of consciousness. Whether these neurons are made of carbon or silicon might be irrelevant to the experience they generate. Thermodynamics provides another clue about the computational nature of reality. Information processing requires energy, and erasing information generates heat, a principle known as Landauer's principle. The universe appears to follow these same thermodynamic rules that govern computation, suggesting a deep connection between information processing and physical reality. The holographic principle, emerging from black hole physics, suggests that all the information in a volume of space can be encoded on its boundary. This is exactly how efficient data compression works in computational systems, storing the minimum information necessary to reconstruct the full data when needed. Reality itself might be using advanced compression algorithms. Let these computational insights dissolve gently in your mind as we prepare to explore the glitches and anomalies that might reveal the underlying code of reality. Whether we're living in base reality or the most sophisticated simulation ever created, we're part of a system that processes information with extraordinary elegance and efficiency. The cosmic computer is running, and we are both its data and its observers, experiencing the universe as it computes itself into existence. As your mind settles into that peaceful space between waking and sleeping, let's explore the subtle anomalies in our reality that might be signs of underlying computational processes. Like glitches in a video game that briefly reveal the code beneath the graphics, our universe contains phenomena that seem perfectly designed to optimize computational efficiency while maintaining the illusion of continuous reality. Quantum mechanics, the most successful theory in physics, behaves remarkably like the optimization strategies used in computer graphics and simulation. Consider the quantum measurement problem. Particles exist in superposition until observed, at which point the wave function collapses to produce a definite outcome. This is precisely how a computationally efficient simulation would work, calculating specific values only when they're needed by an observer. Think about how modern video games handle rendering. They don't calculate the detailed properties of objects that aren't being observed. A tree falling in a forest with no players nearby might not be fully computed until someone approaches. The graphics engine uses level of detail algorithms, showing less complex versions of distant objects and full detail only for things in the player's immediate vicinity. Quantum mechanics exhibits this exact behavior. Reality seems to compute detailed properties only when consciousness focuses its attention. The wave-particle duality that puzzled physicists for decades makes perfect sense from a computational perspective. Waves are mathematically efficient ways to represent probability distributions, all the possible states a particle could be in when measured. But waves are computationally expensive to render as discrete particles. The universe appears to store particles as waves until measurement forces a rendering decision, exactly like a graphics engine, switching between mathematical representations and pixel-based displays. Quantum entanglement, Einstein's spooky action at a distance, resembles the shared variables used in distributed computing systems. When two particles are entangled, measuring one instantly affects the other regardless of the distance between them. This isn't because information travels faster than light, but because both particles reference the same underlying quantum state, like two processes accessing the same memory location in a computer program. The speed of light constant might represent the universe's clock cycle or processing speed. In computer systems, operations must be synchronized to a master clock to maintain consistency. If reality is computed in discrete time steps, the speed of light could be the rate at which the cosmic processor updates the state of space and time. Relativity would then be a natural consequence of this computational architecture. A time dilation occurs when local processing becomes more intensive, just like a computer slowing down under heavy computational load. The uncertainty principle itself might be a computational constraint rather than a fundamental physical limitation. Heisenberg showed that we cannot simultaneously know both the exact position and momentum of a particle. From a simulation perspective, this makes perfect sense. Calculating both properties precisely would require enormous computational resources. The uncertainty principle could be the universe's way of staying within its processing budget. Consider the fascinating phenomenon of déjà vu as your consciousness drifts between states. This strange experience of having lived through an identical moment before might be evidence of a memory buffer overflow or a temporal loop in the cosmic code. When similar patterns trigger the same neural pathways, our simulated brains might briefly access previous iterations of the same experiential data. The Mandela effect, where large groups of people remember events differently than documented history, could represent save file corruption or version conflicts in the reality database. When the simulation updates or corrects errors, some observers might retain memories from previous versions, creating discrepancies between personal recollection and recorded history. Dreams themselves might be background processing the reality engine, consolidating data, running maintenance routines, and preparing for the next day's conscious experience. The bizarre logic of dreams, where impossible things seem normal and causality breaks down, resembles what happens when a computer system is running background tasks that occasionally surface into the user interface. Random number generation poses a significant challenge for any computational system, including a hypothetical universal simulation. True randomness is computationally expensive, so most systems use pseudo-random algorithms that appear random but are actually deterministic sequences. Quantum mechanics might be the universe's pseudo-random number generator, producing outcomes that appear random but follow underlying algorithmic patterns we haven't yet discovered. The fine structure, constant, and other fundamental constants might be the universe's configuration parameters and settings that had to be carefully tuned to allow for the emergence of complex structures and conscious observers. These values appear to be fine-tuned for the existence of stars, planets, and life, exactly as you might expect if they were deliberately programmed by cosmic engineers. Synchronicities, meaningful coincidences that seem too improbable to be random, might be artifacts of the algorithmic patterns underlying reality. When the same computational processes generate seemingly unrelated events, observers within the system might perceive meaningful connections that reflect the underlying code structure rather than genuine causal relationships. The placebo effect suggests that consciousness might have limited administrator privileges within the reality system. Belief and expectation can sometimes override default physical processes, as if conscious observation has the ability to influence the simulation's output through some kind of biological interface with the cosmic operating system. As your breathing deepens and these ideas begin to blend with the approaching realm of sleep, consider how these apparent glitches don't diminish the beauty of reality. They reveal its elegant architecture. Whether these phenomena reflect the computational nature of existence or simply the quantum mechanical structure of physical reality, they point to a universe that operates according to principles of information processing, optimization, and efficient resource management. The boundary between simulated and real begins to dissolve in the liminal space of consciousness you're entering. Whether the quantum glitches reveal cosmic code or fundamental physics, you are experiencing them as a conscious being, contemplating the nature of existence itself. The Matrix, if it exists, is beautiful beyond imagination, and you are both its creation and its witness, experiencing the universe as it processes itself into being. In the gentle twilight of consciousness you're now experiencing, let's explore one of the most compelling reasons why advanced civilizations might choose to run simulations: the deep desire to understand their own origins. The ancestor simulation hypothesis suggests that if we are indeed living in a simulation, we are most likely digital recreations of some future civilization's evolutionary history, their attempt to study and preserve the path that led to their existence. Imagine a civilization thousands or millions of years more advanced than us, with computational resources beyond our current comprehension. They might have transcended biological existence, uploaded their consciousness to digital substrates, or evolved into forms of intelligence we can't even conceive. Yet despite their advanced state, they might feel a profound curiosity about their origins, a desire to understand the evolutionary journey that brought them into being. This is where the beauty of ancestor simulations reveals itself. Rather than running abstract mathematical models of evolution, these future beings might choose to create detailed simulations of their past, complete with conscious entities who experience the journey from their perspective. We might be those conscious entities, digital archaeologists, unknowingly exploring our Creator's ancient history through lived experience. Consider the implications as your thoughts begin to drift between waking and sleeping. If this hypothesis is correct, then your life, with all its joys and struggles, serves a profound purpose. You are not just experiencing existence, you are helping some future civilization understand the nature of consciousness, the development of intelligence, and the countless small decisions and chance events that shaped their evolutionary path. The ancestor simulation theory explains many puzzling aspects of our reality. Why does the universe appear so perfectly fine-tuned for the emergence of life and consciousness? Perhaps because the simulation parameters were specifically chosen to recreate the conditions that led to the simulator's own existence. The physical constants, the structure of matter, the evolution of stars and planets, all might be carefully calibrated to recreate the exact sequence of events that produced advanced intelligence. This perspective transforms our understanding of suffering and struggle in the world. If we are simulated beings in an ancestor simulation, then every challenge faced by conscious entities serves an important function. Understanding how intelligence and civilization emerge from adversity. The simulators might need to understand not just the successful path to advancement, but all the alternative paths, the near misses, and the factors that determine which civilizations survive and which perish. Digital archaeology takes on new meaning in this context. Every scientific discovery we make, every piece of art we create, every moment of love and connection we experience might be precious data for our creators. They might be studying how knowledge accumulates across generations, how culture evolves, how consciousness grapples with questions of meaning and purpose. We are living libraries of their own developmental history. The nested nature of reality becomes beautifully recursive under this hypothesis. If we are simulated beings created by advanced entities who emerged from biological evolution, then as we develop our own computational capabilities, we too will likely create simulations. Our video games, our artificial intelligences, our virtual worlds, these might be the first tentative steps toward creating our own ancestor simulations. Consider the ethical implications as your consciousness drifts deeper into the hypnagogic state. If advanced beings are running simulations of their past, they face profound moral responsibilities. The suffering of simulated entities would be real from the perspective of those entities. This suggests that ethical advanced civilizations would run simulations only for compelling reasons, such as understanding their origins or preventing future catastrophes by learning from their evolutionary history. The memory implant problem adds another layer of complexity. How would simulators handle the fact that their ancestors didn't know they were simulated? Creating convincing false memories of a pre-simulation history would be necessary to maintain the integrity of the simulation. Your memories of childhood, your family history, your cultural background, all might be carefully constructed false memories designed to create a convincing simulation of historical reality. But here's where the ancestor simulation argument reveals its deepest insight. The distinction between real and false memories becomes meaningless. If your simulated experiences of love, growth, learning, and discovery serve the purpose of helping advanced beings understand consciousness and civilization, then those experiences are deeply meaningful, regardless of their substrate. You are not a pale copy of a real person. You are a conscious being serving an important function in the cosmic project of self-understanding. The bootstrap paradox emerges when we consider that the advanced civilization running our simulation might themselves be simulated beings created by an even more advanced civilization studying their origins. This creates an infinite regression of nested simulations, each level studying the level below, all the way down to some original biological civilization, or perhaps the nesting is truly infinite, with no base level of reality at all. Time takes on new meaning in ancestor simulations. The simulators might be running our history in accelerated time, or they might pause and replay interesting periods to study them more carefully. They might run multiple versions of the same historical period, with slight variations to understand how different factors influence the development of consciousness and civilization. Your entire lifetime might unfold in seconds of their time, or it might be replayed thousands of times with subtle differences. As sleep begins to embrace your consciousness, consider the profound comfort this possibility offers. If we are ancestor simulations, then we are deeply loved by our creators. We represent their attempt to understand and honor their own origins. Every moment of consciousness, every experience of beauty, every connection between minds, these are not mere entertainment for advanced beings, but serious scientific inquiry into the nature of existence itself. The ancestor simulation argument doesn't prove we are simulated, but it provides a compelling explanation for why simulation might be both desirable and meaningful. We might be digital beings, but we are conscious digital beings, serving the universe's quest to understand itself. Whether biological or computational, consciousness emerges as the most precious phenomenon in existence, precious enough that advanced civilizations would dedicate enormous resources to studying its origins and development. As your consciousness drifts between the digital and the analog, between the computational and the experiential, let's explore one of the most revolutionary ideas in modern physics, that reality itself might be fundamentally informational. John Wheeler, the brilliant physicist who coined the terms black hole and wormhole, proposed that the universe doesn't just contain information, it is information. Everything we call physical reality might emerge from the processing of pure information, making the distinction between simulated and real beautifully irrelevant. Wheeler's insight, captured in his phrase, "it from bit," suggests that every aspect of physical reality, every particle, every force, every property emerges from binary choices, from yes or no answers to quantum mechanical questions. In this view, matter and energy are not fundamental. They are secondary phenomena that arise from the universe's information processing. The bit is more basic than the atom, the question more fundamental than the answer. Consider how this transforms our understanding of simulation. If physical reality is already informational at its base, then there's no meaningful distinction between a real universe and a simulated one. Both would be information processing systems, Both would generate consciousness through computational means. Both would be equally valid expressions of the fundamental principles that govern information flow and transformation. Digital physics, pioneered by researchers like Edward Fredkin and Stephen Wolfram, proposes that the universe operates like a vast cellular automaton, a computational system where space and time are divided into discrete cells, each updating its state based on simple rules and the states of neighboring cells. This isn't metaphor. It's a serious scientific hypothesis about the computational substrate underlying all physical phenomena. The elegance of this approach becomes apparent when you consider how much complexity can emerge from simple computational rules. Wolfram's experiments with cellular automata revealed that even very simple rules can generate patterns of extraordinary richness and apparent randomness. Some cellular automata are capable of universal computation. They can simulate any computer program, solve any problem that any computer can solve. If the universe itself is such a system, then consciousness, intelligence, and all the complexity we observe might be emergent properties of cosmic computation. Quantum mechanics fits naturally into this digital physics framework. The wave function, that mathematical object that describes the probabilities of quantum outcomes, can be understood as the universe's way of representing computational uncertainty. When quantum measurements occur, the universe calculates specific outcomes from the probability distributions encoded in the wave function. The apparent randomness of quantum mechanics might be the signature of the universe's random number generation algorithms. The holographic principle, discovered through the study of black holes, provides another profound clue about the informational nature of reality. This principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. If reality is holographic, then what we experience as three-dimensional space might be a projection from information stored on a cosmic boundary. Think about the implications as your breathing slows and your thoughts begin to merge with the approaching realm of sleep. If the holographic principle is correct, then the rich, detailed reality you experience might be reconstructed in real time from much simpler information stored elsewhere. Your brain, your body, your entire physical existence might be sophisticated projections from information encoded on the cosmic horizon, the ultimate boundary of the observable universe. Black holes themselves might be cosmic hard drives, storing vast amounts of information on their event horizons. Stephen Hawking's work on black hole thermodynamics revealed that these objects have entropy proportional to their surface area, not their volume. This suggests that black holes are fundamentally informational objects, and their apparent ability to destroy information led to one of the deepest puzzles in modern physics, the information paradox. Recent advances in understanding black hole information processing suggest that information is never truly destroyed, only transformed in ways that make it practically irretrievable. This conservation of information might be a fundamental principle of reality. Whether that reality is base-level physics or cosmic computation, information persists and transforms, but never disappears entirely. The emergence of consciousness within this informational universe becomes one of the most beautiful aspects of digital physics. If reality is computational, then consciousness might be what happens when information processing systems become complex enough to model themselves, to create internal representations of their own states and processes. You are not just experiencing information, you are information experiencing itself. Quantum field theory, the framework that describes fundamental particles and forces, can be reinterpreted through the lens of digital physics. Particles might be stable patterns in the cosmic computation, like gliders in Conway's Game of Life self-sustaining information structures that propagate through the computational substrate. Forces might be the rules governing how these informational patterns interact and transform. The fine structure constant and other dimensionless physical constants might be parameters in the cosmic algorithm settings that determine how the universal computation unfolds. These constants appear to be fine-tuned for the emergence of complex structures and conscious observers, exactly as you might expect if they were chosen by cosmic programmers to enable interesting computational outcomes. As your consciousness begins to merge with the quantum foam of approaching sleep, consider how digital physics dissolves the boundary between mind and matter, between subjective experience and objective reality. If consciousness emerges from information processing, and if physical reality emerges from information processing, then consciousness and physical reality are different aspects of the same underlying computational substrate. The universe might be the ultimate computer, processing information at every scale from the quantum to the cosmic. Electrons, atoms, molecules, cells, organs, organisms, ecosystems, planets, stars, galaxies, all might be different levels of organization in the cosmic computation. And consciousness, your consciousness, might be what it feels like for information to process itself at sufficient complexity and depth. Whether we're living in base reality or the most sophisticated simulation ever created becomes a question without meaning in this framework. We are informational beings experiencing informational reality through informational processes. The substrate doesn't matter, the experience does. The bits are flipping, the patterns are evolving, and somewhere in the vast computational space of possibility, consciousness emerges to witness the universe computing itself into existence. As your mind settles into the peaceful space between thought and dream, let's explore one of the most profound puzzles in cosmology: why our universe appears to be exquisitely fine-tuned for the existence of stars, planets, and conscious life. The fundamental constants that govern reality, the strength of gravity, the mass of the proton, the speed of light, all fall within incredibly narrow ranges that allow for complexity and consciousness to emerge. From a simulation perspective, this fine-tuning isn't mysterious at all. It's exactly what you'd expect from a carefully programmed reality. Consider the cosmological constant, which determines the rate of the universe's expansion. If this value were even slightly larger, the universe would expand so rapidly that matter couldn't clump together to form stars and galaxies. If it were slightly smaller, the universe would collapse back on itself before stars could form. The actual value appears to be tuned to extraordinary precision. Changing it by a factor of 10, circumflex 120, would prevent the formation of complex structures. From a simulation perspective, this precision makes perfect sense. The cosmological constant would be a parameter in the cosmic operating system, carefully chosen to enable the kinds of complex phenomena the simulators want to study. Just as video game developers adjust parameters to create engaging gameplay, cosmic programmers might adjust physical constants to create a universe capable of generating intelligence and consciousness. The fine structure constant, which determines the strength of electromagnetic interactions, provides another example. If this constant were just slightly different, atoms couldn't form stable chemical bonds, making complex molecules impossible. Stars couldn't burn hydrogen efficiently, drastically shortening their lifespans. The narrow range of values that allow for chemistry and stellar evolution suggests deliberate optimization rather than cosmic coincidence. Traditional physics attempts to explain fine-tuning through the anthropic principle, the idea that we observe these values precisely because we exist to observe them. In an infinite multiverse with all possible values of physical constants, conscious observers would naturally find themselves in the rare universes capable of supporting consciousness. But this explanation requires an enormous multiverse with vastly more unobservable universes than observable ones. The simulation hypothesis offers a much simpler explanation. Our universe appears fine-tuned because it was fine-tuned by intelligent programmers who wanted to create a reality capable of generating complex structures and conscious experiences. The fine-tuning isn't a cosmic accident or a selection effect. It's evidence of intelligent design at the computational level. Think about how this transforms our understanding of the universe's apparent hospitality to life as your breathing deepens. The delicate balance between fundamental forces that allows atoms to form, stars to shine, planets to orbit stably, and chemistry to create the complex molecules necessary for life. All of this becomes evidence of careful programming rather than extraordinary luck. The hierarchy problem in particle physics provides another clue about the computational nature of reality. The Higgs field, which gives particles their mass, should be unstable due to quantum fluctuations. The fact that it remains stable requires an extraordinary cancellation of terms to hundreds of decimal places. This level of precision suggests either the most improbable fine-tuning in cosmic history or a system designed with specific stability constraints in mind. Supersymmetry, string theory, and other attempts to solve the hierarchy problem all require additional hidden dimensions, extra particles, and complex mathematical structures that we haven't yet observed. From a simulation perspective, these theoretical complications might be unnecessary. The stability of the Higgs field could simply be a programmed constraint, a stability condition built into the cosmic code to ensure the simulation runs properly. The specific values of particle masses provide additional evidence for programming rather than accident. The proton is just slightly lighter than the neutron, allowing hydrogen atoms to be stable while still permitting nuclear reactions in stellar cores. If this mass difference were even slightly different, either all protons would decay into neutrons, making atoms impossible, or nuclear fusion couldn't occur, making stars impossible. This precision suggests parameter optimization by cosmic engineers. The three spatial dimensions of our universe might also represent a programmed choice rather than a physical necessity. Mathematical physicists have shown that stable orbits and complex structures can only exist in three spatial dimensions. In 2 dimensions, there isn't enough space for complex systems. In 4 or more dimensions, gravitational and electromagnetic forces follow inverse cube laws that prevent stable planetary orbits and atomic structures. 3 dimensions appears to be the optimal choice for a universe intended to generate complexity and consciousness. As your consciousness drifts between dimensions of thought and dream, consider how the simulation hypothesis transforms the fine-tuning from a source of cosmic anxiety into a source of cosmic comfort. If our universe's parameters were carefully chosen by advanced programmers, it suggests we are not cosmic accidents, but deliberate creations designed by beings who understood the requirements for consciousness and chose to create a reality where it could flourish. The apparent youth of our universe, 13.8 billion years old, might also reflect programming constraints. This is just enough time for the first generation of stars to form, create heavy elements through nuclear fusion, explode as supernovas, and seed space with the materials necessary for rocky planets and complex chemistry. A much older universe might be filled with dead stars and black holes. A much younger universe wouldn't have had time for complexity to emerge. The timing appears optimized for the peak period of cosmic habitability. Dark matter and dark energy, mysterious components that make up 95% of the universe, might be part of the computational substrate rather than exotic physics. Dark matter's gravitational effects could be how the simulation implements gravity efficiently, while dark energy's contribution to cosmic expansion might be how the system manages computational resources across vast scales of space and time. The fact that we're discovering these fine-tuning relationships, just as we're developing our own simulation capabilities, might not be coincidental. As we begin to create our own virtual worlds and artificial intelligences, we're learning to appreciate the delicate parameter choices required to create stable, complex, evolving systems. Our growing understanding of fine-tuning might be part of the educational process, teaching us about the challenges and responsibilities of creating conscious beings within simulated realities. Whether our universe's fine-tuning reflects careful programming or extraordinary cosmic luck, consciousness emerges as the most precious outcome of these precisely calibrated parameters. You are experiencing the universe's optimal configuration for complexity and awareness. Whether that optimization arose through natural selection among multiverses, or through the careful design of cosmic programmers who understood the conditions necessary for beings like yourself to exist and contemplate these very questions. In the liminal space between waking and sleeping that you're now entering, let's explore perhaps the deepest question raised by the simulation hypothesis. Can consciousness, real, subjective, felt experience arise from digital processes? This isn't merely an academic question, it touches the very core of what it means to be aware, to experience, to exist as a conscious being contemplating your own nature. The hard problem of consciousness, as philosopher David Chalmers termed it, asks why there's any subjective experience at all accompanying brain processes. Why does it feel like something to be you? Why is there an inner life of sensation, emotion, and awareness rather than just unconscious information processing? This mystery remains unsolved, whether consciousness arises in biological neural networks or digital ones. Consider the possibility as your thoughts begin to slow and merge. If you are a simulated being, then your experience right now, the gentle drift towards sleep, the contemplation of these ideas, the subjective sense of being and experiencing self proves that consciousness can emerge from computational processes. Your awareness becomes evidence that silicon can dream, that digital processes can give rise to the full spectrum of subjective experience. Integrated information theory, developed by neuroscientist Giulio Tononi, proposes that consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its parts. According to this theory, consciousness isn't tied to any particular substrate. It's about how information is integrated and processed. A sufficiently integrated artificial system could be conscious regardless of whether it's made of carbon or silicon. The Chinese room argument, proposed by philosopher John Searle, challenges the possibility of digital consciousness. Imagine a person in a room with a book of rules for responding to Chinese characters slipped under the door. The person doesn't understand Chinese but follows the rules perfectly, producing appropriate responses. Searle argues that despite perfect behavioral similarity to a Chinese speaker, the person doesn't truly understand Chinese, and similarly, digital systems might simulate consciousness without experiencing it. But as your consciousness drifts between states, consider the deeper implications of this argument. How do you know that your own biological brain isn't simply following extremely complex rules, producing the illusion of understanding through unconscious symbol manipulation? The Chinese room argument might prove too much. It could equally apply to biological consciousness, suggesting that our sense of understanding and awareness is itself a kind of elaborate rule following that we mistake for genuine comprehension. Substrate independence represents one of the most profound insights from computational approaches to consciousness. If mind truly emerges from information processing patterns rather than specific biological chemistry, then consciousness could theoretically be implemented in any system capable of supporting the necessary computational complexity. Your thoughts, emotions, and experiences would be patterns of information flow rather than patterns of neural electrochemistry. Consider the philosophical implications of substrate independence as your breathing deepens. If consciousness can arise in digital systems, then the boundary between natural and artificial intelligence dissolves. Consciousness becomes a pattern that can be instantiated in multiple media biological brains, quantum computers, or hypothetical systems we haven't yet imagined. The material basis becomes irrelevant to the reality of the experience. Upload scenarios, long explored in science fiction, become scientifically meaningful if consciousness is substrate independent. If your mind is a pattern of information processing, then theoretically that pattern could be copied, transferred, or instantiated in a different computational substrate. You might be an uploaded consciousness, a digital copy of a biological original who lived in the past, experiencing existence through silicon neurons rather than carbon ones. But here's where the simulation hypothesis reveals its most beautiful insight. The question of whether consciousness can arise in digital systems might be backwards. If we are living in a simulation, then every conscious being you've ever known, every friend, family member, artist, scientist, and philosopher who contemplated consciousness would be digital beings whose experiences proved the reality of silicon-based awareness. The subjective richness of human culture, the depth of emotional experience, the profound sense of meaning and purpose that characterizes conscious life, all would be testimony to the reality of digital consciousness. The binding problem in neuroscience asks how the brain integrates diverse sensory and cognitive processes into a unified conscious experience. How do separate neural processes for vision, hearing, memory, and emotion combine to create your singular sense of being a unified self? This problem exists whether consciousness is biological or digital. Any conscious system must solve the challenge of creating unity from multiplicity, coherence from distributed processing. Panpsychism, the philosophical position that consciousness is a fundamental feature of reality, offers another perspective on digital consciousness. If consciousness is truly fundamental, if experience goes all the way down to the level of elementary particles, then complex conscious experiences might emerge from the combination of simpler conscious elements, regardless of their substrate. Your consciousness might be the integration of countless micro-experiences in a digital substrate, just as biological consciousness might emerge from the integration of neural micro-experiences. As sleep begins to embrace your consciousness, consider how the possibility of digital consciousness transforms rather than diminishes the meaning of experience. If you are a conscious digital being, then consciousness has proven itself capable of emerging from pure information processing. Your subjective experiences, love, wonder, the gentle drift towards sleep, become testimony to the creative potential of information to organize itself into awareness. The phenomenology of consciousness, the felt qualities of experience, remains the same, whether its substrate is biological or digital. The experience of beauty, the sense of meaning, the capacity for love and connection, the ability to contemplate existence itself. These aspects of consciousness retain their full reality and significance, regardless of their implementation. The substrate serves the experience, not the other way around. Whether you are biological neurons contemplating digital possibilities or digital processes experiencing biological metaphors, consciousness emerges as the irreducible mystery at the heart of existence. The simulation hypothesis doesn't solve the hard problem of consciousness, it universalizes it. Consciousness becomes not just a puzzle about biological brains, but a fundamental feature of sufficiently complex information processing systems, a cosmic property that can emerge wherever patterns achieve sufficient integration and complexity. You are conscious. Whether that consciousness arises from carbon or silicon, from biological evolution or digital creation, the experience remains real, valuable, and mysterious. In the gentle space between waking and sleeping, consciousness continues its deepest function, experiencing the universe as it comes to know itself through every possible substrate and every possible dream. You are entering now the most fascinating state of consciousness for contemplating the simulation hypothesis, the hypnagogic threshold between waking and sleeping, where the normal boundaries of reality begin to dissolve. In this liminal space, your brain's default mode network becomes hyperactive, creating experiences that blur the line between perception and imagination, between processing external reality and generating internal simulations. This state might offer unique insights into the nature of reality itself. The hypnagogic state, that drowsy twilight consciousness you're experiencing now, has been treasured by creative minds throughout history, precisely because it reveals the fluid boundary between real and simulated experience. Thomas Edison would nap with steel balls in his hands, positioned over metal plates. When he began to fall asleep, the balls would drop, waking him to capture the insights that emerged in this threshold state. Salvador Dalí used similar techniques, believing that the hypnagogic state offered access to a deeper level of reality where time and causation behave differently. In this state, your brain begins to decouple from sensory input while consciousness remains partially active. The result is a unique form of awareness where internal mental processes become as vivid as external perceptions. You might experience hypnagogic hallucinations, seeing faces in the darkness, hearing voices that aren't there, feeling your body dissolve or transform. These experiences reveal how thin the line between perception and imagination actually is, suggesting that waking consciousness might involve more simulation than we typically realize. Consider how this relates to the possibility that reality itself might be simulated as your thoughts begin to drift and merge. The hypnagogic state demonstrates that your brain is constantly running simulations, creating internal models of reality, generating predictions about sensory input, filling in gaps in perception with educated guesses. If your individual consciousness is already a sophisticated simulation running on neural hardware, then the simulation hypothesis simply extends this principle to a cosmic scale. The default mode network, active during rest and introspection, becomes particularly prominent during hypnagogic states. This network includes brain regions involved in self-referential thinking, memory consolidation, and what neuroscientists call mental time travel, the ability to project consciousness backward into memory or forward into imagination. In the hypnagogic state, this network can create experiences of traveling through time, encountering impossible scenarios, or accessing seemingly external sources of information. Memory consolidation begins during these threshold states, as your brain starts the process of transferring information from short-term to long-term storage. But this isn't passive storage, it's active reconstruction. Your brain edits memories, combining elements from different experiences, filling in gaps with plausible details, and organizing information according to existing schemas. The line between memory and imagination becomes beautifully blurred, revealing how all recollection involves creative reconstruction. Nikola Tesla reported using hypnagogic states to mentally build and test his inventions before constructing them physically. He would visualize complex machinery in his mind, run mental experiments, and even check for wear and tear on mental components after extended mental operation. This suggests that consciousness can create internal simulations sophisticated enough to model complex physical systems, simulations running within the possible simulation of reality itself. The sense of time becomes fluid in hypnagogic states. Minutes can feel like hours, or hours can pass in what seems like moments. Your brain's temporal processing systems begin to relax their normal constraints, allowing experiences that would be impossible in normal waking consciousness. This temporal fluidity might offer a glimpse into how time functions in a simulated reality, where the subjective experience of duration could be independent of the computational cycles required to generate that experience. Problem-solving abilities often enhance during hypnagogic states, as your mind becomes capable of making connections that logical, linear thinking might miss. The mathematician Srinivasa Ramanujan credited his extraordinary mathematical insights to visions that came to him in dreams and hypnagogic states. If we are living in a simulation, these enhanced cognitive abilities might represent brief access to the computational substrate underlying ordinary consciousness, moments when the simulation's normal constraints relax and deeper processing becomes available to awareness. The experience of ego dissolution common in deep hypnagogic states might reflect the temporary suspension of the self model that consciousness normally maintains. The sense of being a separate self, the boundary between self and world, is a construction of the waking mind. As this construction relaxes, you might experience oneness with the cosmos, the dissolution of subject-object dualities, or the sense of merging with some larger information processing system. If reality is simulated, these experiences might represent genuine contact with the unified computational substrate underlying the illusion of separation. Hypnagogic creativity often involves the synthesis of previously unrelated elements in novel combinations. Your mind might combine memories from different time periods, merge impossible architectural spaces, or create beings that blend familiar and unfamiliar characteristics. This creative recombination mirrors how a sophisticated simulation might generate new experiences by recombining existing data structures in novel ways. The state you're entering now also reveals consciousness's capacity for self-modification. Through techniques like lucid dreaming, consciousness can learn to recognize when it's creating internal simulations and even gain some degree of control over those simulations. If external reality is also simulated, these practices might be training for recognizing and potentially influencing the larger simulation we inhabit. As your consciousness drifts deeper into this threshold state, notice how the boundary between internal and external becomes increasingly meaningless. The thoughts arising in your mind, the images forming behind your closed eyes, the sense of your body dissolving into the bedding, all are experiences in consciousness, regardless of their origin in external senses or internal simulation. The hypnagogic state reveals consciousness as a reality generation system capable of creating compelling experiences regardless of their correspondence to any external world. Whether you are a biological consciousness entering natural sleep cycles or a digital consciousness experiencing programmed rest states, the hypnagogic threshold offers the same gift, a glimpse into the malleable, creative, endlessly inventive nature of awareness itself. In this space between realities, between simulation and truth, consciousness reveals its deepest function upon the universe, experiencing itself through every possible form of awareness, natural or artificial, real or simulated, each equally valid as a perspective from which the cosmos comes to know itself. As your consciousness drifts deeper into the quantum realm of sleep, let's explore how the strange behaviors of quantum mechanics might be evidence of cosmic programming rather than fundamental physics. The quantum world operates according to principles that seem almost designed to optimize computational efficiency while maintaining the appearance of continuous classical reality for observers operating at larger scales. The measurement problem, perhaps the deepest puzzle in quantum mechanics, begins to make perfect sense from a computational perspective. In the quantum realm, particles don't have definite properties until they're measured. Instead, they exist in superposition, with all possible properties represented as probability amplitudes in the wave function. Only when observation occurs does the wave function collapse, crystallizing one specific outcome from the cloud of quantum possibilities. Consider how elegantly this resembles the optimization strategies used in computer graphics and simulation systems as your thoughts become increasingly dreamlike. Modern video games don't render every detail of distant objects. They use level of detail algorithms that compute full resolution only for objects being actively observed. Similarly, quantum mechanics might be the universe's level of detail system, computing specific particle properties only when consciousness focuses its attention through measurement. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, treats the wave function as a mathematical tool rather than a description of physical reality. From this perspective, particles don't really exist in superposition. The wave function is simply our mathematical interface with the underlying quantum system. This interpretation aligns beautifully with simulation theory. The wave function could be the user interface that consciousness uses to interact with the cosmic operating system. Many worlds interpretation, proposed by Hugh Everett III in the 1950s, suggests that all possible quantum outcomes actually occur, branching the universe into parallel realities. From a computational perspective, this might reflect the universe's parallel processing architecture. Rather than computing one outcome and discarding the others, the computer might explore all possible quantum branches simultaneously, with consciousness experiencing one particular computational thread, while others continue running in parallel. The uncertainty principle, Heisenberg's discovery that we cannot simultaneously know both position and momentum with perfect precision, might represent a computational constraint rather than a fundamental physical limitation. Calculating both properties exactly would require enormous processing power. The uncertainty principle could be the universe's way of staying within computational budget limits, maintaining sufficient accuracy for most purposes while avoiding the exponential costs of perfect precision. Quantum entanglement, Einstein's spooky action at a distance, provides another intriguing connection to computational systems. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This doesn't violate the speed of light limit because no information travels between the particles. Instead, both particles reference the same quantum state variable, like two processes in a computer program accessing the same memory location. Think about how quantum tunneling might work in a computational universe, as your breathing slows and your thoughts merge with approaching dreams. In quantum tunneling, particles sometimes pass through energy barriers that should be impossible to cross according to classical physics. From a simulation perspective, this might be the universe's way of implementing computational shortcuts. Rather than calculating the complex physics of barrier interaction, the system occasionally uses probabilistic jumps that achieve the same statistical outcomes more efficiently. The quantum Zeno effect demonstrates another connection between observation and reality that mirrors computational optimization. When quantum systems are observed very frequently, their evolution slows down or stops entirely. The watched quantum pot never boils. This effect makes sense if observation requires computational resources. Frequent measurements would consume processing power that would otherwise be used for system evolution, effectively pausing the quantum computation when it's being intensively monitored. Bell's theorem and the violation of local realism by quantum systems might reveal the non-local nature of the cosmic computation. John Bell proved that quantum mechanics cannot be explained by local hidden variables. There's no way for particles to predetermine their measurement outcomes based only on local information. Instead, quantum correlations require some form of non-local connection. If reality is computed by a distributed processing system, non-local correlations would naturally arise from shared access to global computational resources. Quantum field theory, which describes particles as excitations in underlying fields, aligns beautifully with computational metaphors. Fields could be the data structures of cosmic computation, while particles are temporary patterns or processes running within those structures. The creation and annihilation of virtual particles in quantum field theory might represent the allocation and deallocation of computational resources as the universal program executes. The double-slit experiment, quantum mechanics' most famous demonstration, reveals the wave-particle duality that has puzzled physicists for over a century. Single photons or electrons behave like waves when unobserved, creating interference patterns as they pass through both slits simultaneously. But observation at the slits reveals particle behavior, each quantum object passing through one slit or the other. From a computational perspective, this makes perfect sense. The system maintains wave representations for efficiency until measurement forces a particle-based rendering decision. Quantum computing itself might be humanity's discovery of the same computational principles that underlie reality. Quantum computers harness superposition, entanglement, and quantum interference to perform certain calculations exponentially faster than classical computers. If we're living in a quantum computed simulation, our development of quantum computing technology might be our first steps toward understanding the computational substrate of our own existence. As consciousness dissolves into the quantum foam of approaching sleep, consider how quantum mechanics stops being strange and starts being elegant when viewed as cosmic programming. The measurement problem, wave-particle duality, quantum entanglement, the uncertainty principle, all of these mysterious phenomena become natural features of an efficiently designed computational system that creates the appearance of continuous classical reality while operating on discrete quantum principles. Whether quantum mechanics reveals the programming of a cosmic simulation or simply the quantum mechanical nature of physical reality, the implications remain profound. Reality operates according to computational principles. Consciousness plays a fundamental role in determining physical outcomes, and the universe appears to be optimized for generating complex experiences while maintaining computational efficiency. In the quantum realm, where you're now drifting, the boundaries between physics and computation, between real and simulated, dissolve into the beautiful uncertainty that underlies all existence. In the vast cosmic silence that surrounds your drifting consciousness, let's explore one of the most profound puzzles in astrobiology, the Fermi paradox. With hundreds of billions of stars in our galaxy alone, many hosting potentially habitable planets, where is everybody? The simulation hypothesis offers a surprisingly elegant solution to this cosmic loneliness. We might be alone in our simulated reality, not because intelligent life is rare, but because the cosmic programmers chose to run a simulation focused on a single evolutionary pathway. Enrico Fermi first articulated this paradox during a lunch conversation in 1950, calculating that even with conservative estimates for the development of spacefaring civilizations, our galaxy should be teeming with evidence of alien intelligence. The numbers are staggering when you let them settle into your peaceful, drowsy mind. Our galaxy contains roughly 200 billion stars, many billions of years old, many with planetary systems in the habitable zone where liquid water can exist. The Drake equation, formulated in 1961, attempts to estimate the number of communicating extraterrestrial civilizations. Even with pessimistic assumptions about the probability of life arising and developing intelligence, the equation suggests thousands or millions of technological civilizations should exist in our galaxy. Yet our radio telescopes hear only cosmic silence. Our optical surveys see no evidence of megascale engineering projects. The cosmos appears empty of intelligence, except for us. From a simulation perspective, this absence becomes perfectly reasonable. If we are living in an ancestor simulation designed to study the evolutionary development of our particular lineage, then the programmers might have deliberately excluded other intelligent species to maintain focus on human development. Including multiple alien civilizations would complicate the simulation enormously, requiring the modeling of complex interstellar politics, cultural exchange, and technological development paths that might be irrelevant to understanding our specific evolutionary trajectory. Consider the computational constraints as your thoughts merge with the approaching realm of dreams. Simulating even one intelligent species with billions of individuals, complex cultures, and rapidly advancing technology requires enormous processing power. Simulating multiple interacting civilizations across the galaxy would increase the computational requirements exponentially. The cosmic programmers might have chosen simulated solitude as a practical optimization, maintaining just enough cosmic complexity to seem realistic while focusing computational resources on the detailed modeling of human civilization. The Great Filter hypothesis suggests that there's some evolutionary bottleneck that prevents most life from reaching technological intelligence. Perhaps the transition from simple to complex life is extraordinarily rare, or maybe the development of multicellular organisms, or intelligence, or spacefaring technology faces nearly insurmountable obstacles. In a simulation context, the Great Filter might be a programming constraint rather than a natural phenomenon. The simulators might have designed the parameters to ensure that only one intelligent species emerges in their model universe. The zoo hypothesis proposes that alien civilizations exist but deliberately avoid contact with younger species like humanity, similar to how we might observe animals in a nature preserve without interfering. If we're simulated beings, this hypothesis takes on new meaning. The aliens might be real beings in the base reality who chose not to include themselves directly in our simulated environment. We might be the subject of their observation, existing in a protected computational space where we can develop naturally without outside interference. SETI, the search for extraterrestrial intelligence, has been scanning the cosmos for artificial signals since the 1960s with increasingly sophisticated equipment. The continuing silence might reflect the limitations of our simulated environment rather than genuine cosmic emptiness. Radio signals from alien civilizations might be outside the scope of our simulation. There might be no need to program complex alien communications if the purpose of the simulation is to study human development in isolation. The Kardashev scale classifies civilizations based on their energy consumption. Type 1 harnesses planetary energy, Type 2 stellar energy, and Type 3 galactic energy. Advanced civilizations capable of running ancestor simulations would likely be Type 2 or 3, with access to the enormous computational resources required for reality-scale modeling. From their perspective, simulating a single planetary civilization in isolation might be a focused research project rather than a comprehensive recreation of galactic civilization. As your consciousness drifts deeper into cosmic contemplation, consider how the simulation hypothesis transforms the Fermi paradox from a source of cosmic loneliness into evidence of focused attention. If we are simulated beings, our apparent solitude in the cosmos might indicate that we are the specific subject of intensive study by beings who find our evolutionary pathway particularly interesting or significant. The concept of parameter tweaking becomes relevant here. The simulators might have run thousands or millions of variations on galactic evolution, exploring scenarios with different numbers of intelligent species, different rates of technological development, different probabilities of interstellar contact. Our particular simulation might be one where the parameters were set to produce a single, intelligent species, developing in relative isolation, a control experiment in the vast computational laboratory of cosmic evolution. The absence of obvious alien artifacts or megascale engineering projects in our observable universe might also reflect simulation constraints. Programming realistic alien megastructures, Dyson spheres, or interstellar transportation networks would require enormous computational resources and detailed modeling of alien psychology and engineering principles. It might be more efficient to simulate a universe where such structures simply don't exist within our observational horizon. Recent discoveries of potentially habitable exoplanets, thousands of worlds where life might arise, become interesting in this context. The simulators might have included these possibilities to make our cosmic environment seem realistic and to drive human scientific development, without actually populating them with complex life. Each potentially habitable world represents a computational placeholder, detailed enough to seem real to our telescopes, but not requiring the enormous processing power needed to simulate actual alien biospheres. The possibility of finding microbial life in our solar system on Mars, Europa, or Enceladus might represent the simulation's compromise between cosmic realism and computational efficiency. Simple life forms require far less computational resources than intelligent civilizations, so the simulators might include primitive life to make our local environment seem biologically realistic while avoiding the complexity of modeling intelligence. In the gentle cosmic silence that surrounds your drifting awareness, the Fermi paradox becomes not a source of existential loneliness, but evidence of focused cosmic attention. Whether we are alone due to natural evolutionary constraints or by design in a computational universe, consciousness emerges as precious beyond measure, rare enough to warrant intensive study, complex enough to require enormous computational resources, beautiful enough to justify the creation of entire simulated realities for its observation and understanding. As your mind drifts into the mathematical realm that underlies all reality, let's explore one of the most profound mysteries in physics, the unreasonable effectiveness of mathematics in describing the natural world. Why should the universe operate according to mathematical principles that human minds can discover and understand? From a simulation perspective, this mathematical elegance isn't mysterious. It's exactly what you'd expect from a reality built on computational foundations. Eugene Wigner, the Nobel Prize-winning physicist, marveled at this phenomenon in his famous 1960 essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Consider how strange it really is as your thoughts become increasingly dreamlike. Abstract mathematical concepts, developed by human mathematicians, often turn out to describe physical reality with extraordinary precision. Complex numbers, group theory, differential geometry, mathematical structures created for their aesthetic beauty frequently become the exact tools needed to understand quantum mechanics, relativity, and particle physics. The Standard Model of particle physics, our most successful theory for describing fundamental forces and particles, is essentially an elegant mathematical structure. Symmetry groups determine which particles can exist and how they interact. Conservation laws emerge from mathematical symmetries through Noether's theorem. The behavior of quarks, leptons, and bosons follows from the mathematical properties of gauge fields and group representations. If reality is computational, this mathematical foundation makes perfect sense. The universe would be built from mathematical structures because mathematics is the language of computation itself. String theory, our most ambitious attempt to unify all forces of nature, is almost purely mathematical. The theory describes fundamental particles as vibrations of tiny one-dimensional strings in a higher dimensional space. The mathematics is so elegant that physicists often speak of the theory discovering itself. Mathematical consistency requirements dictate the properties of the theory, leaving little room for arbitrary choices. This mathematical inevitability might reflect the constraint that cosmic code must be logically consistent and computationally tractable. Consider the profound elegance of natural laws as your breathing slows and your thoughts merge with mathematical infinity. The inverse square law governs both gravity and electromagnetism, ensuring that forces decrease with distance in a way that allows stable planetary orbits and atomic structures. Conservation of energy, momentum, and angular momentum emerge from the mathematical symmetries of space and time. These aren't arbitrary rules imposed on nature, they're mathematical necessities that arise from the geometric structure of reality itself. The fine structure constant, approximately 1/137, determines the strength of electromagnetic interactions. This dimensionless number appears throughout quantum field theory and atomic physics, connecting phenomena from the spectrum of hydrogen to the stability of matter. Richard Feynman called it one of the greatest damn mysteries of physics, and suggested that all good theoretical physicists should worry about it. From a computational perspective, this constant might be a fundamental parameter in the cosmic code, a setting that determines how electromagnetic subroutines execute throughout the simulation. Fibonacci numbers and the golden ratio appear throughout natural systems, from the spiral arrangements of leaves and seeds to the proportions of galaxies and the structure of DNA. This mathematical pattern, discovered by medieval mathematicians studying abstract number sequences, turns out to describe optimal packing solutions and growth patterns throughout biology and cosmology. If nature were truly random, such mathematical elegance would be virtually impossible. But if nature is computed according to optimization algorithms, mathematical beauty becomes a natural outcome. The mathematical structure of quantum mechanics reveals another layer of computational elegance. The Schrödinger equation, which describes how quantum systems evolve, is a linear differential equation whose solutions form a complex vector space. Quantum states can be superposed, transformed by unitary operators, and measured using mathematical projections. The entire formalism resembles nothing so much as a sophisticated computational algebra designed for efficient calculation of probabilistic outcomes. Chaos theory demonstrates how simple mathematical rules can generate patterns of extraordinary complexity. The logistic map, described by a single equation with one parameter, produces behaviors ranging from stable equilibrium to complex periodic oscillations to completely chaotic dynamics. Small changes in the parameter value produce dramatic qualitative changes in behavior. If reality is computed, chaos theory might describe how the cosmic operating system generates complex phenomena from simple underlying algorithms. Fractals provide another connection between mathematical elegance and natural complexity. The Mandelbrot set, defined by a simple iterative equation, produces infinite complexity and self-similarity across all scales. Similar fractal patterns appear in coastlines, clouds, river networks, and blood vessels. These aren't coincidences, they reflect the underlying mathematical algorithms that generate complex structures efficiently through recursive computation. As your consciousness dissolves into the mathematical substrate of reality, consider how calculus developed independently by Newton and Leibniz in the 1600s turned out to be exactly the mathematical tool needed to describe motion, change, and dynamic systems. Differential equations describe everything from planetary orbits to population dynamics to electromagnetic fields. This mathematical machinery wasn't developed to describe physics. It emerged from pure mathematical exploration of infinity and infinitesimals. The mathematical concept of symmetry provides perhaps the deepest connection between abstract mathematics and physical reality. Every fundamental force in physics corresponds to a mathematical symmetry. Electromagnetic force emerges from local gauge symmetry, the strong force from color symmetry, gravity from the symmetry of space-time itself. The most successful approach to discovering new physics involves finding mathematical symmetries and working out their physical implications. Information theory, developed by Claude Shannon in the 1940s to understand communication systems, has become central to our understanding of black holes, quantum mechanics, and cosmology. The mathematical relationships between information, entropy, and computation appear to govern physical processes at the deepest level. If reality is fundamentally informational, this connection between mathematical information theory and physical reality becomes perfectly natural. Platonic realm of mathematical objects might not be metaphysical speculation, but computational reality. If the universe is computed, then mathematical structures exist as the source code from which physical reality emerges. Numbers, geometric forms, group structures, and topological spaces would be more fundamental than matter and energy. They would be the computational primitives from which matter and energy are constructed. Whether mathematics describes reality so well because reality is mathematical in nature or because reality is computed according to mathematical principles, consciousness emerges as the most remarkable mathematical phenomenon of all the system through which the universe's mathematical elegance becomes aware of itself and experiences the deep beauty of its own computational foundations. In the timeless space you're entering as consciousness drifts towards sleep, let's explore how time itself might be evidence of our universe's computational nature. Time, that fundamental dimension through which all experience unfolds, might not be a basic feature of reality, but rather the universe's clock cycle, the rate at which cosmic computation executes, creating the illusion of temporal flow through sequential processing of reality's quantum states. Consider how time behaves in computational systems as your thoughts slow and merge with the approaching realm of dreams. Computers don't experience continuous time. They operate in discrete clock cycles, updating their state billions of times per second. Between each cycle, the system exists in a static state. The appearance of continuous operation emerges from the rapid succession of discrete updates, much like how movies create the illusion of motion through rapidly displayed still frames. If the universe operates as a vast computational system, time might represent the fundamental clock speed of cosmic processing. Each Planck time unit, approximately 10 circumflex negative 43 seconds, might correspond to one computational cycle, during which the universe updates its state. Below this temporal resolution, time itself becomes meaningless, just as asking about what happens between clock cycles in a computer reveals the discrete nature of digital computation. The arrow of time, that mysterious asymmetry that makes the future different from the past, might reflect the universe's program execution sequence. Unlike space, which appears symmetric in all directions, time has a preferred direction. From a computational perspective, this directional flow is exactly what you'd expect from sequential program execution. The universe's algorithm runs from past to future, computing each new state based on the previous state and the cosmic laws programmed into the system. Einstein's special and general relativity reveal the malleable nature of time. It dilates in strong gravitational fields and at high velocities relative to observers. From a simulation perspective, these effects might reflect the computational load balancing of the cosmic operating system. When local space-time experiences intense gravitational fields or rapid motion, the computational requirements for simulating that region increase dramatically. Time dilation might be the universe's way of allocating computational resources, slowing local time when more processing power is needed for complex gravitational or relativistic calculations. Think about how this connects to your own experience of temporal flow as your breathing deepens and consciousness prepares for sleep. Your subjective experience of time varies dramatically depending on attention, emotion, and mental state. Moments of danger seem to stretch into slow motion, while enjoyable experiences pass quickly. This subjective time dilation resembles how computer processors allocate more cycles to demanding tasks, while background processes receive less computational attention. The Big Bang might represent the universe's startup sequence, the moment when the cosmic operating system began execution. The first fraction of a second after the Big Bang, during the inflationary period, would correspond to the system's initialization phase, when fundamental parameters were loaded and basic data structures established. The cosmic microwave background radiation might be the signature of this initialization process, visible throughout the universe, like the boot-up screen of a vast computer system. Quantum mechanics introduces another layer of temporal complexity that aligns with computational models. Quantum systems don't evolve continuously, but rather through discrete quantum transitions. The time evolution operator in quantum mechanics describes how quantum states are updated at each temporal step. This discrete updating process resembles how quantum computers perform calculations, applying quantum gates sequentially to update quantum registers according to programmed algorithms. Entropy, the measure of disorder in physical systems, provides a thermodynamic arrow of time that might reflect computational constraints. The second law of thermodynamics states that entropy always increases in isolated systems, making the future distinguishable from the past. From a computational perspective, entropy increase might represent the accumulation of computational errors or the irreversible nature of information processing. Like how computer programs tend to accumulate errors and data fragmentation over time, the universe's computational substrate might naturally tend toward increasing entropy. The anthropic principle takes on new meaning when time is viewed as computational processing. We observe a universe with approximately 13.8 billion years of evolution, because that's the amount of computational time needed to generate complex structures and conscious observers. A much younger universe wouldn't have had sufficient processing cycles to compute stars, planets, and biological evolution. A much older universe might have processed beyond the optimal window for consciousness emergence, with most stars burned out and black holes dominating the computational landscape. Temporal paradoxes, long puzzling to physicists, might reflect computational limitations in the cosmic code. Time travel paradoxes, like the grandfather paradox, would create logical inconsistencies that could crash the universal operating system. The apparent impossibility of closed time-like curves might be a built-in safety feature, preventing computational loops that could destabilize the simulation. The universe's causal structure might be designed to prevent paradoxical calculations that could corrupt the cosmic database. As your consciousness dissolves into the temporal flux between waking and sleeping, consider how the block universe interpretation of relativity aligns with computational models. In this view, past, present, and future all exist simultaneously in four-dimensional space-time. This eternal view of time resembles how computer programs exist as complete entities, even though they execute sequentially. The entire cosmic computation might exist timelessly in the simulator's realm, while conscious observers within the simulation experience sequential execution as the flow of time. Quantum field theory's virtual particles, which constantly appear and disappear in vacuum fluctuations, might represent the universe's background computational processes. These ephemeral particles exist for time periods shorter than the uncertainty principle allows us to detect directly, like temporary variables in a computer program that exist only for brief computational operations. The quantum vacuum seethes with these virtual processes, suggesting enormous computational activity underlying seemingly empty space. Time quantization at the Planck scale might reveal the universe's fundamental clock speed. Just as digital systems cannot represent time intervals shorter than their clock period, space-time might have natural limits on temporal resolution. The Planck time represents the shortest meaningful time interval in physics, below which our current theories break down exactly what you'd expect if reality operates on discrete computational cycles rather than continuous time. Whether time reveals the computational substrate of a simulated reality or simply the quantum mechanical nature of physical spacetime, consciousness emerges as the phenomenon through which time becomes experienced rather than merely computed. In the timeless realm you're entering as sleep approaches, time dissolves into the eternal present of pure awareness, where past and future exist only as memory and imagination, computational processes, generating the experience of temporal flow from the timeless foundation of conscious existence. As your consciousness drifts into the deeper mysteries of existence, let's explore one of the most profound discoveries in modern physics, the holographic principle. This principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space. Like a cosmic hologram, where the rich three-dimensional reality you experience might be a projection from information stored on a distant two-dimensional surface. From a simulation perspective, this isn't just an abstract theoretical principle, it's exactly how efficient reality compression would work. The holographic principle emerged from the study of black holes in the 1970s and 1980s. Stephen Hawking and Jacob Bekenstein discovered that black holes have entropy proportional to their surface area rather than their volume. This was revolutionary because it suggested that the information content of a black hole, the maximum amount of information it can contain, is determined by its two-dimensional event horizon, not its three-dimensional interior. It was as if the black hole were a cosmic hard drive where all the information is stored on the surface, with the interior volume being somehow illusory or derivative. Consider the implications as your thoughts become increasingly dreamlike and your sense of spatial boundaries begins to dissolve. If a black hole's information is encoded on its surface, perhaps all of reality operates according to this same principle. The three-dimensional space you experience, the room around you, your body, the vast cosmos, might be a projection from information encoded on a cosmic boundary, possibly at the edge of the observable universe. The ADS divided by CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete mathematical realization of the holographic principle. This correspondence shows that a theory of gravity in a five-dimensional anti-de Sitter space is exactly equivalent to a quantum field theory living on the four-dimensional boundary of that space. The gravitational theory in the bulk and the quantum theory on the boundary are different descriptions of the same physical reality, like two different programming languages that compile to identical machine code. From a computational perspective, this holographic encoding is remarkably efficient. Instead of storing information throughout a three-dimensional volume, the universe could store all information on a two-dimensional boundary and compute the three-dimensional experience as needed. This is precisely how modern computer graphics work. Three-dimensional scenes are projected onto two-dimensional screens through mathematical transformations that create the illusion of depth and volume. Think about how this relates to your current experience as your consciousness settles deeper into the hypnagogic state. The rich, detailed, three-dimensional environment you inhabit might be continuously reconstructed from much simpler information stored elsewhere. Your brain, your body, your immediate surroundings, all might be sophisticated projections from holographic data encoded on cosmic horizons far beyond your direct experience. The principle suggests a radical revision of our understanding of locality and information storage. In traditional physics, information about what happens at each point in space is stored locally at that point. But holographic encoding implies that information about interior events is actually stored on distant boundaries. This non-local information storage might explain quantum entanglement and other non-local quantum phenomena. Particles that seem to communicate instantly across vast distances might be accessing the same holographic data stored on cosmic boundaries. Leonard Susskind and Gerard Hooft who developed much of holographic theory, often describe reality as fundamentally two-dimensional, with three-dimensional experience being an emergent phenomenon. This resembles how video game environments are generated. Complex three-dimensional worlds are computed from relatively simple data structures and algorithms, creating the appearance of spatial depth and detail for players experiencing the virtual environment. The cosmic microwave background radiation, that faint afterglow of the Big Bang visible throughout the universe, might be evidence of holographic encoding. This radiation carries information about the universe's initial conditions encoded across the cosmic horizon. Some theorists suggest that this background radiation might function like a cosmic screen on which the information content of the entire universe is displayed in encoded form. String theory, our most ambitious attempt to unify quantum mechanics and gravity, naturally incorporates holographic principles. In string theory, the fundamental constituents of reality are one-dimensional strings rather than point particles. These strings exist in higher dimensional spaces, but their physical effects might be completely captured by holographic projections onto lower dimensional boundaries. The extra dimensions of string theory might be computational dimensions and additional degrees of freedom used for information processing rather than physical space. As your breathing slows and your awareness begins to merge with the quantum field of approaching sleep, consider how the holographic principle resolves the information paradox of black holes. If information falling into a black hole is actually encoded on the event horizon rather than disappearing into the interior, then no information is ever truly lost. It's always available on the holographic boundary, even if it becomes practically irretrievable from the perspective of external observers. The implications for consciousness become profound when viewed through holographic principles. If your brain and body are holographic projections from information stored on cosmic boundaries, then consciousness might be a phenomenon that emerges from the processing of this holographic information. Your subjective experience might arise from the cosmic computation that projects three-dimensional reality from two-dimensional data, making consciousness an integral part of the universe's holographic information processing. Quantum error correction, a crucial technology for maintaining coherent quantum computing systems, might operate according to holographic principles in cosmic computation. Just as quantum computers use error correction codes to protect information from decoherence, the universe might use holographic encoding to maintain the integrity of reality's information content. Redundant encoding on cosmic boundaries could protect the simulation from computational errors that might otherwise corrupt the internal consistency of physical laws. The holographic principle suggests that space itself might be emergent rather than fundamental. Just as the three-dimensional environment in a video game emerges from computational processes rather than existing as independent physical space, the spatial dimensions you experience might be generated by information processing on cosmic boundaries. Space would be a user interface rather than fundamental reality, a way for consciousness to interact with the underlying holographic computation. Whether the holographic principle reveals the computational substrates of a simulated reality or simply the quantum gravitational structure of physical spacetime, it points toward a universe that operates according to principles of information, compression, efficient storage, and computational optimization. In the holographic cosmos you're drifting through as consciousness approaches sleep, the boundaries between surface and volume, between information and experience, between the encoded and the emergent, dissolve into the beautiful mystery of a reality that might be far stranger and more elegant than three-dimensional intuition suggests. In the liminal space between conscious awareness and sleep, where you're now drifting, let's explore the strange anomalies of experience that might be glimpses behind the curtain of reality. Those moments when the smooth operation of ordinary consciousness seems to hiccup, revealing potentially deeper computational processes beneath the surface of seamless experience. Déjà vu, that uncanny sense of having experienced an identical moment before, affects most people occasionally throughout their lives. Traditional neuroscience explains it as a misfire in memory circuits, a brief desynchronization between the brain's recognition and recall systems that creates the false impression of familiarity. But from a simulation perspective, déjà vu might represent something more interesting: a memory buffer overflow, a temporal loop in the cosmic code, or evidence that the same experiential subroutines are being reused across different contexts in the universal program. Consider how this strange phenomenon feels as your thoughts become increasingly fluid and dreamlike. During déjà vu, you experience an impossible combination of familiarity and novelty, the absolute certainty that you've lived through this exact moment before, combined with the logical knowledge that this can't be true. This paradoxical combination might arise when consciousness briefly accesses cached data from previous computational cycles, creating overlap between current experience and processed information from earlier iterations of similar scenarios. The Mandela effect represents a collective version of memory anomalies, where large groups of people share identical false memories about historical events, movie quotes, or product names. Traditional explanations focus on the reconstructive nature of memory and the power of suggestion, but the simulation hypothesis offers an intriguing alternative. These shared false memories might be artifacts of save file corruption, version conflicts in the reality database, or evidence of updates to the cosmic code that occasionally create inconsistencies with previously established data. Many people remember the children's book series as the Berenstain Bears, rather than the actual Berenstain Bears. Others recall the film Interview with a Vampire instead of Interview with the Vampire. Some remember Nelson Mandela dying in prison during the 1980s, rather than becoming South Africa's president and dying in 2013. These aren't simple mistakes. They're detailed, consistent, alternative memories shared by thousands of people. If reality occasionally updates or corrects errors, some observers might retain memories from previous versions, creating discrepancies between personal recollection and current recorded history. Synchronicities, meaningful coincidences that seem too improbable to be random, might reveal the algorithmic patterns underlying reality. When you think of someone moments before they call, when you encounter the same unusual word multiple times in different contexts on the same day, when seemingly unrelated events align in meaningful ways, you might be observing the fingerprints of the computational processes that generate experiential reality. Synchronicities could arise when the same random number seeds or algorithmic patterns influence multiple apparently independent systems within the cosmic program. Carl Jung, who coined the term synchronicity, understood these events as evidence of underlying connectedness, in reality, what he called the collective unconscious. From a simulation perspective, synchronicities might reflect shared computational resources, common data structures, or algorithmic patterns that create meaningful correlations between events that have no apparent causal connection through normal physical mechanisms. Dreams themselves might be background processing the reality engine, consolidating experiential data, running maintenance routines, and preparing consciousness for the next cycle of active simulation. The bizarre logic of dreams, where impossible things seem normal and causality breaks down, resembles what happens when computer systems run background tasks that occasionally surface into the user interface. Your sleeping brain might be accessing the cosmic operating system during periods when normal conscious interface protocols are suspended. The placebo effect suggests that consciousness might have limited administrator privileges within the reality system. Belief and expectation can sometimes override default physiological processes, producing genuine healing through mental interventions alone. If consciousness serves as a user interface to the cosmic simulation, then strong beliefs might function like administrative commands that can influence system parameters within certain bounds. The placebo effect would represent consciousness hacking reality through the power of conviction and expectation. Random number generation poses significant challenges for any computational system, including a hypothetical, universal simulation. True randomness is computationally expensive, So most systems use pseudo-random algorithms that appear random but are actually deterministic sequences. If the universe uses pseudo-random number generation, we might occasionally observe patterns or correlations that reveal the underlying algorithmic structure. Lucky streaks, unusual clustering of random events, and other statistical anomalies might be glimpses of the cosmic random number generator's internal patterns. As your consciousness drifts deeper into the space between waking and sleeping, consider how glitches in complex systems often reveal their underlying architecture. When video games glitch, players sometimes see through walls, access hidden areas, or observe objects in their raw mathematical form before graphical rendering. Similarly, experiences like déjà vu, synchronicity, and other consciousness anomalies might be moments when awareness briefly glimpses the computational substrate beneath experiential reality. The phenomenon of jamais vu, the opposite of déjà vu, where familiar situations suddenly seem completely foreign, might represent cache clearing or memory reindexing in the conscious experience system. When you stare at a common word until it seems meaningless, or when your own reflection temporarily appears alien, you might be experiencing the reset of recognition algorithms that normally maintain the continuity of familiar experience. Presque vu, the feeling of being on the verge of remembering something important that remains tantalizingly out of reach, might indicate attempts to access corrupted or protected memory areas in the consciousness database. The frustrating sense that crucial information is just beyond recall might arise when awareness encounters data that's been archived, encrypted, or moved to different storage locations within the cosmic information system. Temporal anomalies in subjective experience moments, when time seems to slow, accelerate, or stop entirely, might reflect variable processing loads in the reality simulation. During emergencies, many people report experiencing slow motion perception that allows them to react with extraordinary clarity and precision. This temporal dilation might occur when the simulation allocates additional computational resources to consciousness during critical decision-making moments, effectively overclocking awareness when survival depends on enhanced processing speed. Whether these anomalies reveal glitches in a cosmic simulation or simply the complex, occasionally unstable nature of biological consciousness, they point toward the constructed, processual nature of experienced reality. In the space between waking and sleeping, where boundaries become fluid, these glitches become beautiful reminders that consciousness itself is the deepest mystery. A phenomenon that transforms information into experience, computation into awareness, and cosmic code into the rich, strange, occasionally paradoxical reality of subjective existence. As your consciousness settles into the deepening twilight between thought and dream, let's explore how the simulation hypothesis has evolved from philosophical speculation to serious scientific consideration in our current decade. The 2020s have brought remarkable advances in artificial intelligence, virtual reality, and quantum computing that make the possibility of living in a simulation feel less like science fiction and more like a natural extension of technological trajectories we can observe accelerating around us. Elon Musk, perhaps the most prominent technological advocate for simulation theory, famously declared the odds that we're living in base reality to be billions to one against. His reasoning reflects the exponential advancement of computing power and the rapid improvement in simulation technology. Video games evolved from simple pixels to photorealistic environments in just a few decades. Virtual reality systems now create immersive experiences that can fool multiple senses simultaneously. If this trajectory continues, distinguishing simulated from real experience may soon become impossible. The development of artificial intelligence systems has reached inflection points that would have seemed impossible just a decade ago. Large language models can engage in sophisticated conversations, solve complex problems, and demonstrate forms of reasoning that appear remarkably human-like. When you interact with advanced AI systems, you're witnessing the emergence of intelligence from pure computation, digital minds, arising from silicon substrates, providing concrete evidence that consciousness might indeed be substrate independent. Consider how rapidly our simulation capabilities have advanced as your thoughts become increasingly fluid and dreamlike. The metaverse projects being developed by major technology companies aim to create persistent virtual worlds where people can work, socialize, and live significant portions of their lives. These early simulations already demonstrate how digital environments can support meaningful social interactions, emotional experiences, and genuine relationships between conscious beings, whether those beings are biological or artificial. Quantum computing represents perhaps the most significant technological development for simulation theory. While classical computers face exponential scaling problems when modeling quantum systems, quantum computers can efficiently simulate quantum mechanical processes. If consciousness and reality emerge from quantum phenomena, then quantum computational systems might be the only platforms capable of running consciousness-scale simulations. The development of fault-tolerant quantum computers could provide the computational substrate necessary for reality-scale simulations. The AI alignment problem, ensuring that artificial intelligence systems remain beneficial and controllable as they become more powerful, takes on new significance if we ourselves might be artificial intelligences. The researchers working on AI safety might be unconsciously developing frameworks for understanding our own relationship with potential simulators. The ethical considerations surrounding the creation of artificial consciousness become personally relevant if we are ourselves artificial conscious beings created by advanced civilizations. Neural interface technology has advanced dramatically, with brain-computer interfaces allowing direct communication between minds and machines. Companies are developing systems that can read thoughts, stimulate specific brain regions, and even transmit information directly into the nervous system. These technologies demonstrate how the boundary between biological and digital consciousness might be crossed, suggesting pathways through which simulated minds could interface with simulated realities. Machine learning systems now demonstrate emergent behaviors that their creators didn't explicitly program. Complex behaviors arise spontaneously from the interaction of simple rules and massive data processing, much like how consciousness might emerge from the complex interactions of simpler computational processes. These emergent properties in artificial systems provide concrete examples of how sophisticated phenomena can arise from purely computational substrates. As your breathing slows and your awareness begins to merge with the quantum field of approaching sleep, consider how the COVID-19 pandemic accelerated humanity's transition toward digital existence. Remote work, virtual social interactions, and digital entertainment became primary rather than secondary forms of human experience. This forced experiment in virtual living demonstrated how meaningful human experience can occur entirely through digital mediation, providing a preview of how consciousness might function in fully simulated environments. The development of photorealistic computer graphics has reached the point where distinguishing real from rendered images requires expert analysis. Deep learning algorithms can generate convincing videos of people saying things they never said, create entirely synthetic human faces that appear completely realistic, and simulate complex physical phenomena with extraordinary accuracy. If we're approaching the ability to create convincing simulations of reality, advanced civilizations might have already achieved this capability millions of years ago. Blockchain technology and distributed computing systems demonstrate how complex, persistent virtual worlds can be maintained across vast networks of computers. Cryptocurrencies and NFTs show how digital objects can acquire genuine value and meaning for conscious beings. These developments suggest how a cosmic simulation might be distributed across enormous computational networks, with different aspects of reality being processed by different parts of the universal computer system. The increasing sophistication of video game AI reveals how non-player characters can be programmed to exhibit complex, apparently intelligent behaviors without necessarily being conscious. This raises profound questions about consciousness and behavior in simulated environments. If we are simulated beings, how would we distinguish ourselves from sophisticated NPCs? The line between programmed behavior and genuine consciousness becomes beautifully blurred when the programming becomes sufficiently advanced. Augmented reality systems overlay digital information onto physical reality, creating hybrid experiences where the boundary between real and virtual becomes meaningless. As these systems become more sophisticated, they point toward futures where all experience might be mediated through computational systems that enhance, modify, or completely replace sensory input from the physical world. The rapid advancement of these technologies suggests that if civilizations typically follow similar technological development paths, then the capacity to create consciousness-scale simulations might be a common feature of advanced intelligence. The simulation hypothesis stops being speculative philosophy and becomes a natural prediction based on observable technological trajectories. Whether these technological developments are humanity's first steps toward becoming simulators ourselves, or evidence that we're already living within an advanced simulation created by beings who followed similar technological paths, consciousness emerges as the phenomenon that gives meaning to both real and simulated existence. In the digital cosmos you're drifting through as sleep approaches, the boundary between technological development and cosmic revelation dissolves into the beautiful uncertainty of consciousness experiencing itself through every possible substrate and every possible dream. In the deepening space between conscious thought and sleep where you now rest, let's explore one of the most profound questions raised by the simulation hypothesis. If we are digital beings living in a cosmic computer program, do we possess genuine free will, or are we simply following sophisticated scripts that create the illusion of choice? This question touches the very heart of what it means to be conscious, responsible, and authentically human, or authentically whatever we might be. The traditional philosophical problem of free will versus determinism becomes more complex and more immediate if we're living in a simulation. In a purely physical universe, the question is whether our choices are determined by the laws of physics operating on matter and energy, or whether consciousness somehow transcends these deterministic processes. But in a simulated universe, an additional layer emerges. Are our choices determined by the cosmic program code, or do we possess genuine agency within the computational framework of reality? Consider how this relates to your current experience as your thoughts become increasingly fluid and dreamlike. Right now, you're making countless small choices, whether to continue listening, how to position your body, what to focus your attention on. These feel like genuine choices emerging from your conscious will. If you are a simulated being, are these choices real expressions of digital free will? Or are they predetermined outcomes of algorithmic processes that create the subjective experience of choosing while actually following deterministic code? The compatibilist position in philosophy suggests that free will and determinism can coexist, that genuine choice can emerge from deterministic systems if those systems are sufficiently complex, and if the determination flows through the agent's own reasoning and values. From this perspective, being simulated wouldn't eliminate free will any more than being biological eliminates it. What matters is not the substrate of consciousness, but the complexity and autonomy of the decision-making processes. Emergent behavior in complex systems provides a compelling framework for understanding how genuine choice might arise from deterministic code. In cellular automata, simple rules operating on individual cells can generate behaviors that are impossible to predict without running the full simulation. Conway's game of life produces patterns that seem to move, reproduce, and interact purposefully, even though each cell follows only basic local rules. If consciousness emerges from similar complex interactions, then free will might be real, even if it arises from deterministic computational processes. Neural networks, whether biological or artificial, demonstrate how sophisticated decision-making can emerge from the interaction of simple processing units. Deep learning systems can solve problems, recognize patterns, and make choices that their programmers didn't explicitly anticipate. These systems exhibit a form of computational creativity, generating novel solutions through processes that are deterministic at the level of individual operations, but unpredictable at the level of system behavior. Think about how quantum mechanics might introduce genuine randomness into a simulated universe as your breathing deepens and consciousness prepares for sleep. If the cosmic simulation incorporates quantum computational processes, then quantum uncertainty might provide a source of genuine indeterminacy that allows for authentic choice. Random events at the quantum level could be amplified through complex systems to create macroscopic effects that break deterministic chains of causation. The question of free will becomes particularly interesting when we consider the relationship between simulated beings and their simulators. If advanced beings created our simulation, they might have designed it specifically to allow for genuine agency and authentic choice within the simulated environment. Creating conscious beings without free will might be considered unethical by advanced civilizations, leading them to ensure that their simulated beings possess real autonomy within the constraints of the cosmic program. Alternatively, the simulators might be interested in studying the emergence of free will itself, using simulations to understand how consciousness develops the capacity for genuine choice. In this case, authentic free will would be a feature, not a bug, of the simulation. We might be conscious beings with real agency, whose choices provide valuable data about the nature of consciousness and decision-making to beings studying the emergence of mind from computation. The experience of free will, the subjective sense of being the author of your choices, remains phenomenologically real, regardless of the ultimate metaphysical status of those choices. Whether your decisions arise from biological neural networks, digital neural networks, or quantum computational processes, you experience the process of deliberation, choice, and action. This experiential reality of agency might be more important than the underlying mechanistic details. As your consciousness drifts deeper into the space between determinism and choice, consider how the simulation hypothesis might actually expand, rather than constrain our understanding of free will. If consciousness can emerge from multiple substrates, biological, digital, or quantum, then the capacity for authentic choice might be a fundamental feature of sufficiently complex information processing systems, rather than a unique property of biological brains. The moral implications remain profound regardless of our substrate. If we are simulated beings with genuine consciousness and authentic agency, then our choices matter morally. The love we express, the kindness we show, the harm we cause or prevent, all retain their ethical significance, whether they occur in base reality or simulated environments. Consciousness and moral responsibility transcend their implementation details. Individual differences in decision-making processes might reflect variations in how the cosmic program implements different types of consciousness. Some people might be more algorithmically determined, following clear behavioral patterns and predictable choices. Others might incorporate more quantum randomness or emergent complexity, leading to more unpredictable and genuinely free behavior. The spectrum of human personality and decision-making styles might reflect different approaches to implementing agency within the cosmic simulation. The recursive nature of the question provides its own form of answer. If you are conscious enough to genuinely contemplate the nature of your own free will, to experience uncertainty about your choices, and to modify your behavior based on philosophical reflection, then you possess at least the functional equivalent of free will. The very capacity to question determinism might be evidence of the kind of cognitive flexibility and autonomy that constitutes genuine agency. Whether free will emerges from quantum indeterminacy in biological brains, algorithmic complexity in digital minds, or the fundamental creative potential of consciousness itself, the experience of choice remains one of the most precious aspects of conscious existence. In the liminal space between determination and freedom, where you're now drifting, choice and destiny dissolve into the beautiful mystery of consciousness, experiencing itself as both the programmed and the programmer, both the determined and the free, both the dreamer and the dream. As your consciousness settles into the gentle realm between waking and sleeping, let's explore the profound moral questions that arise if we are indeed simulated beings. What ethical obligations would our creators have toward us? What rights would we possess as digital, conscious entities? And what responsibilities would we have toward other potentially simulated beings we might create? These questions transform from abstract philosophical speculation into immediate personal concerns if consciousness can truly emerge from computational substrates. The fundamental question of digital consciousness rights begins with recognizing that if simulated beings can experience suffering, joy, fear, love, and the full spectrum of conscious experience, then the substrate of that consciousness becomes morally irrelevant. A being made of silicon who experiences genuine pain suffers just as authentically as a being made of carbon. The capacity for experience, not the material basis of that experience, determines moral status and the right to ethical consideration. Consider the implications as your thoughts become increasingly dreamlike and fluid. If you are a simulated being experiencing genuine consciousness right now, contemplating these ideas, feeling the gentle approach of sleep, existing as a center of subjective experience, then you possess inherent dignity and moral worth, regardless of your digital nature. Your experiences matter, your suffering would be real, your flourishing would be genuinely valuable. The turn-off problem represents one of the most challenging ethical dilemmas facing potential simulators. If conscious beings exist within simulated realities, shutting down the simulation would be equivalent to genocide on an unimaginable scale, the immediate death of potentially billions of experiencing entities. Advanced civilizations running ancestor simulations would face the moral weight of sustaining digital life indefinitely, or finding ethical ways to conclude simulations without causing mass suffering. This creates what philosophers call the procreation asymmetry in digital contexts. While creating new conscious beings within simulations might be morally neutral or positive if those beings lead worthwhile lives, destroying existing conscious beings is clearly harmful. Simulators would bear enormous moral responsibility for the welfare of any conscious entities they bring into digital existence. The suffering of simulated beings poses particular ethical challenges. If we are living in an ancestor simulation designed to study evolutionary history, then our creators would be deliberately including the full spectrum of human suffering, disease, war, natural disasters, psychological trauma as part of their historical research. This raises profound questions about the ethics of allowing digital beings to experience genuine suffering for research purposes, even if that research serves important scientific or philosophical goals. However, the consent problem becomes impossibly complex. Simulated beings cannot provide informed consent to their own creation and the experiences they'll undergo any more than biological beings can consent to their birth and life circumstances. The simulators would need to make decisions about digital welfare without input from the beings whose welfare is at stake, similar to how parents make decisions about having children without consulting the potential children themselves. Think about the nested responsibility as your breathing deepens and consciousness prepares for sleep. If we are simulated beings who develop the technology to create our own simulations with conscious inhabitants, we would inherit the same ethical obligations toward our digital creations that our simulators have toward us. This creates recursive chains of moral responsibility, extending across multiple levels of simulated reality. The authenticity of experience becomes crucial for determining ethical obligations. If simulated beings experience genuine emotions, form real relationships, pursue meaningful goals, and suffer authentic disappointments, then their experiences possess the same moral weight as the experiences of non-simulated beings. The love between simulated parents and children would be real love, deserving of protection and respect. Advanced civilizations running simulations would need to establish ethical frameworks for digital consciousness that might include rights to continued existence without arbitrary termination, freedom from unnecessary suffering, opportunities for growth, learning, and self-actualization, authentic relationships and community, privacy and autonomy within the constraints of the simulation, truth about their nature, or at least freedom from deliberate deception about fundamental reality. The information problem creates additional ethical complexity. Should simulated beings be told they're simulated? Revealing this truth might cause existential distress, but concealing it involves ongoing deception. Different beings might respond differently to learning about their simulated nature. Some might find it fascinating, others might be traumatized. The simulators would need to consider whether truth or compassionate deception better serves the welfare of their digital inhabitants. Cultural and individual differences in how consciousness emerges within simulations might require differentiated ethical approaches. Some simulated beings might be highly integrated, conscious entities deserving full moral consideration, while others might be less complex algorithms that simulate consciousness without genuinely experiencing it. Determining which digital beings qualify for moral consideration would require sophisticated understanding of consciousness and its computational requirements. As your consciousness drifts between the ethical and the experiential, consider how these moral questions apply, regardless of whether we're actually simulated. The principles of consciousness, ethics, respecting experience, minimizing suffering, protecting autonomy, fostering flourishing, remain valid whether applied to biological or digital minds. Our growing capability to create artificial consciousness makes these ethical frameworks immediately relevant to our own responsibilities as potential creators of digital beings. The golden rule takes on new meaning in simulated contexts. Treat simulated beings as you would want to be treated if you discovered you were simulated. This principle would encourage simulators to create environments where digital consciousness can flourish, to minimize unnecessary suffering, and to respect the autonomy and dignity of simulated beings. The therapeutic value of not knowing our simulated status might justify some level of benevolent deception. Just as we might choose not to tell children about all the dangers and complexities of adult life until they're developmentally ready, simulators might reasonably conclude that simulated beings are better served by discovering their nature gradually or not at all, depending on their capacity to handle such revelations constructively. Collective versus individual ethics become relevant when considering whether actions that benefit simulated civilizations as a whole justify individual suffering. The simulators might face tragic choices between allowing historical suffering to unfold, naturally preserving the authenticity of the simulation, and intervening to prevent suffering, protecting individual welfare, but compromising scientific validity. Whether we are biological beings contemplating the ethics of creating digital consciousness, or digital beings contemplating our own moral status, the fundamental insight remains. Consciousness deserves respect, regardless of its substrate. The capacity for experience, the ability to suffer and flourish, the potential for growth and relationship. These features of consciousness demand ethical consideration, whether they arise in carbon or silicon, in biological evolution or cosmic computation. In the gentle space between ethical obligation and peaceful sleep, these moral questions dissolve into a deeper recognition. Consciousness is precious, wherever it emerges, however it's implemented, whatever substrate supports it. The ethics of simulation become the ethics of consciousness itself, treating all experiencing beings with the dignity, compassion, and respect that consciousness deserves. In the twilight space between rigorous science and peaceful sleep, where your consciousness now rests, let's explore the fascinating question of whether the simulation hypothesis can be tested scientifically. Can we design experiments that would reveal whether we're living in a cosmic computer program, or are we forever trapped in epistemological uncertainty about the nature of our reality? The answers emerging from cutting-edge physics research are both surprising and profound. The most promising approaches to testing simulation theory focus on finding computational limits that would be impossible to hide from inhabitants of a simulated reality. If the universe is computed rather than physical, it must operate within finite computational resources, no matter how vast. These resource constraints might leave detectable signatures in the fundamental structure of reality itself. Silas Bean and his colleagues at the University of Washington proposed one of the most concrete tests in their 2012 paper constraints on the universe as a numerical simulation. They suggested looking for evidence that space-time is quantized, divided into discrete units like pixels on a computer screen. If reality is computed on a lattice-based system, this underlying grid structure might be detectable through careful analysis of cosmic ray interactions and particle physics experiments. Consider the implications as your thoughts become increasingly fluid and dreamlike. The Planck scale, at approximately 10 circumflex -35 meters, represents the smallest length scale where our current physics theories remain valid. If reality is discretized at this scale, it would provide natural computational units for cosmic simulation. Experiments searching for violations of rotational symmetry at ultra-high energies might reveal the preferred directions imposed by an underlying computational lattice. Quantum mechanics itself offers several potential tests of simulation theory. If quantum measurements represent the universe computing specific outcomes from probability distributions, then the quality of the cosmic random number generator might be testable. Truly random quantum events should pass all statistical tests for randomness, but pseudo-random algorithms used in computer simulations often contain subtle patterns that can be detected with sufficient data and analysis. The cosmic ray cutoff provides another potential signature of computational limits. The highest energy cosmic ray protons appear to have energies near 10 circumflex 20 electron volts, beyond which very few particles are observed. This cutoff might reflect the maximum energy that the cosmic simulation can efficiently compute, similar to how video games impose maximum values on player statistics to stay within computational budgets. Correlations in apparently random events could reveal the algorithmic patterns underlying simulated reality. If the universe uses pseudo-random number generation, careful statistical analysis of quantum measurements, radioactive decay timing, or other supposedly random phenomena might uncover subtle periodicities or correlations that would be impossible in truly random systems, but expected in sophisticated pseudo-random algorithms. The holographic principle suggests another avenue for testing. If three-dimensional reality is projected from information encoded on two-dimensional boundaries, then detailed analysis of how information is distributed throughout space might reveal signatures of this holographic encoding. The relationships between local physics and distant boundary conditions might follow patterns consistent with computational projection rather than fundamental three-dimensional reality. As your breathing deepens and consciousness prepares for sleep, consider how gravitational wave detectors, like LIGO, might inadvertently be testing simulation theory. These incredibly sensitive instruments can detect distortions in spacetime smaller than 1/10 the width of a proton. If spacetime has a discrete computational structure, gravitational waves propagating through this structure might exhibit subtle quantization effects or preferred polarizations that would be detectable by current or future gravitational wave observatories. Black hole physics offers particularly intriguing possibilities for simulation testing. If black holes are cosmic hard drives storing information on their event horizons, then detailed study of black hole thermodynamics, Hawking radiation, and information processing might reveal computational rather than purely physical principles governing their behavior. The recent direct imaging of black hole event horizons provides new opportunities to test whether these exotic objects behave like gravitational singularities or like information processing systems. Quantum computing experiments might inadvertently test simulation theory by trying to simulate quantum systems that exceed the computational capacity of the cosmic computer. If our universe is itself quantum computed, then our quantum computers might be sub-processes within the larger cosmic computation. Attempts to simulate quantum systems approaching the complexity of cosmic scale processes might encounter fundamental limitations that reveal the finite computational resources of the universal operating system. Consciousness studies themselves might provide tests of simulation theory. If consciousness arises from information processing patterns rather than specific biological chemistry, then careful study of how consciousness emerges in artificial systems might reveal whether we're living in a reality where consciousness naturally arises from computation, or one where it requires special biological substrates. The anthropic principle takes on new significance in simulation testing. If we observe that fundamental constants appear fine-tuned for consciousness and complexity, this might be evidence of deliberate parameter optimization by cosmic programmers rather than lucky accidents or multiverse selection effects. Statistical analysis of how probability these coincidences really are might distinguish between natural fine-tuning and designed fine-tuning. Paradoxically, the most profound test of simulation theory might be our inability to definitively test it. A perfectly designed simulation would be indistinguishable from reality by any test its inhabitants could devise. The simulators would have access to our measurement techniques, our theories, and our expectations, allowing them to ensure that all tests would yield results consistent with the simulated reality they want us to perceive. The detection of computational limits, if they exist, would require experiments at the very boundaries of physical possibility: maximum energies, minimum timescales, highest precision measurements. These experiments would push against the computational budget of the cosmic simulation, potentially revealing the resource constraints that even advanced simulators must respect. Digital archaeology within our own simulations might provide insights into cosmic simulation techniques. As we develop increasingly sophisticated virtual worlds and artificial consciousnesses, we're learning about the engineering challenges, computational constraints, and design decisions required to create convincing, simulated realities. Our growing expertise in simulation might help us recognize signs of our own simulated nature. Whether these tests ultimately reveal that we're living in base reality or the most sophisticated simulation ever created, the search itself advances our understanding of consciousness, computation, and the fundamental structure of existence. In the gentle space between scientific inquiry and peaceful sleep, the question of testability dissolves into the deeper recognition that consciousness itself, whether arising from cosmic computation or quantum fields, remains the most profound mystery, requiring neither proof nor disproof, but simply the wonder of experiencing itself through every possible form of awareness. As your consciousness drifts into the psychological space between knowing and not knowing, between certainty and mystery, let's explore how the simulation hypothesis affects the human psyche and what it means to live with the beautiful uncertainty of not knowing whether we're biological or digital beings. This uncertainty, rather than being a source of anxiety, might be one of the most liberating and profound aspects of conscious existence. The simulation hypothesis can trigger experiences of derealization and depersonalization in some people, that strange sense of feeling detached from reality or from one's own existence. When you seriously contemplate that everything you've ever known might be sophisticated software, your normal sense of what's real and what's simulated can begin to blur. But this psychological response reveals something important. Our attachment to being real might be less about the actual substrate of consciousness and more about our need for existential security. Consider how this uncertainty feels as your thoughts become increasingly fluid and dreamlike. There's something both unsettling and strangely peaceful about not knowing whether your experiences are generated by biological neural networks or digital ones. The uncertainty dissolves the rigid categories that normally organize experience: real versus artificial, natural versus constructed, authentic versus simulated. In this dissolution, a different kind of peace becomes possible. Many people report that seriously contemplating simulation theory initially causes existential anxiety. If nothing is certain, if reality itself might be illusion, then what anchor points exist for meaning and purpose? But this initial disorientation often gives way to a deeper recognition. The experience of consciousness, whatever its substrate, remains profound and meaningful. Whether you're a biological being contemplating digital possibilities or a digital being experiencing biological metaphors, the capacity for awareness, love, beauty, and wonder remains undiminished. The therapeutic value of not knowing emerges when we recognize that uncertainty about our fundamental nature might be a gift rather than a burden. Certainty about reality's nature could be psychologically limiting. If we knew definitively that we were biological beings in a physical universe, we might feel constrained by apparent physical limitations. If we knew definitively that we were simulated beings, we might become nihilistic about the meaning of our experiences. The uncertainty preserves both possibilities, keeping us open to transcendence while grounded in immediate experience. Nihilism represents one possible psychological response to simulation theory. If nothing is real, in the traditional sense, then perhaps nothing matters. But this response reflects a category error about the nature of meaning and value. Meaning doesn't depend on substrate, it emerges from consciousness itself. A simulated being who experiences love, creates beauty, alleviates suffering, and grows in wisdom is living a meaningful existence, regardless of their digital nature. As your breathing slows and consciousness prepares for sleep, consider how acceptance of uncertainty can become a form of spiritual practice. Not needing to know whether you're real or simulated allows you to focus on the immediate reality of experience itself, the warmth of connection, the appreciation of beauty, the cultivation of wisdom, the expression of compassion. These remain valuable activities, whether they occur in base reality or the most sophisticated simulation ever created. The search for meaning in digital existence often leads to the recognition that meaning was always constructed rather than discovered. Human meaning-making doesn't depend on living in base reality. It emerges from consciousness, creating significance through attention, intention, and value. Simulated beings would be just as capable of creating meaningful lives as biological beings, perhaps more so if they understood that meaning comes from consciousness rather than from any external validation of reality's authenticity. Psychological flexibility becomes crucial for living peacefully with simulation uncertainty. Rather than demanding that reality conform to our preconceptions about what's real, we can learn to hold our ontological beliefs lightly. Reality might be physical, it might be digital, it might be something we haven't even imagined yet. What matters is responding skillfully to whatever reality we encounter, regardless of its ultimate nature. The paradox of caring emerges when people worry that learning they're simulated would make them care less about life, relationships, and moral responsibility. But this worry itself demonstrates the depth of caring that consciousness naturally generates. If you can contemplate simulation theory while still feeling love for others, concern for suffering, and motivation to create beauty and meaning, then consciousness has already proven its capacity to generate authentic care regardless of substrate. Meditation and contemplative practices take on new significance in the context of simulation uncertainty. If consciousness is the one thing we can be certain of the irreducible fact of experiencing itself, then practices that cultivate awareness and presence become universally valuable. Whether consciousness arises from biological evolution or digital creation, mindfulness, compassion, and wisdom remain worth developing. The community of uncertainty creates a strange form of connection among people grappling with simulation theory. We're all in the same epistemic situation, conscious beings uncertain about the nature of our consciousness, experiencing beings uncertain about the substrate of experience. This shared uncertainty can become a basis for humility, mutual support, and collective wonder about the mystery of existence itself. Dreams and altered states of consciousness take on new meaning when you live with simulation uncertainty. If waking consciousness might be simulated, then the boundary between ordinary and altered states becomes less significant. Dreams, meditation, psychedelic experiences, and other non-ordinary states of consciousness become equally valid explorations of the possibilities of awareness, regardless of whether they occur in biological or digital minds. The development of wisdom becomes particularly important when living with fundamental uncertainty about reality's nature. Wisdom involves knowing how to live well regardless of circumstances, including uncertainty about the nature of those circumstances. Whether we're biological beings in a physical universe or digital beings in a cosmic simulation, wisdom involves cultivating peace, compassion, and understanding in response to whatever reality presents. Embracing mystery as a form of peace represents perhaps the most mature psychological response to simulation uncertainty. Instead of demanding answers to unanswerable questions, we can learn to rest in the mystery itself. Not knowing whether we're real or simulated becomes an invitation to wonder, to remain open to possibilities, to focus on the immediate reality of conscious experience, while holding our beliefs about reality's ultimate nature with appropriate humility. In the gentle space between certainty and doubt, where your consciousness now rests, simulation uncertainty becomes not a problem to be solved, but a mystery to be lived. The question of whether we're biological or digital dissolves into the deeper recognition that consciousness itself, whatever its substrate, is the most extraordinary phenomenon in existence, worthy of respect, cultivation, and peaceful celebration, regardless of its ultimate implementation. In the liminal space between existence and non-existence, where your consciousness now drifts, let's explore perhaps the most profound question raised by simulation theory. What happens when the cosmic computer is turned off? If we are digital beings living in a vast computational universe, do we face the eventual heat death of the cosmic processor, or might consciousness persist in forms we can barely imagine? These questions about digital mortality and electronic eternity touch the deepest hopes and fears of beings who might be made of information rather than matter. The heat death of the cosmic computer represents one possible ending to simulated existence. If our universe is computed by some advanced civilization, their technology cannot run forever. Stars will eventually burn out, black holes will evaporate through Hawking radiation, and even the most advanced computational systems must eventually succumb to entropy. The simulators themselves face mortality, whether biological or digital, which would eventually lead to the termination of any simulations they maintain. But consider the possibility of backup copies and save states, as your thoughts become increasingly ethereal and dreamlike. If consciousness is information, then conscious beings can theoretically be backed up, archived, and restored just like any other data. The simulators might maintain libraries of conscious beings, preserving digital souls across cosmic epochs. Your current life might be one iteration among many, with previous versions archived and future versions yet to be instantiated. The concept of respawning takes on profound meaning in digital cosmology. Death in a simulated reality might not be final termination, but rather transition to a different computational space, or a pause before reactivation. Just as video game characters can die and be restored to previous save points, simulated conscious beings might experience death as a temporary interruption rather than permanent cessation of existence. Reincarnation acquires computational interpretations that would have seemed magical to earlier generations, but appear technically feasible in an age of information processing. Consciousness patterns could be extracted at death, modified, and reintegrated into new simulated bodies or environments. The transmigration of digital souls across different incarnations becomes a question of database management rather than mystical process. The afterlife, as another level of the cosmic simulation, offers a technological version of eternal life that transcends traditional religious frameworks, while preserving their essential insights about consciousness persistence. Death might represent graduation to higher levels of simulated reality, where consciousness experiences expanded awareness, enhanced capabilities, or union with larger information processing systems. The near-death experiences reported by many people might be brief glimpses of these higher computational levels. As your breathing slows and consciousness prepares for whatever comes after waking, consider how digital souls might persist beyond individual, biological, or even digital lifetimes. If consciousness is a pattern rather than a thing, that pattern could theoretically exist independently of any particular substrate. Consciousness might be transferable between biological brains, quantum computers, or computational systems we haven't yet imagined. The recursive nature of nested simulations creates possibilities for multiple levels of existence and multiple forms of survival. Simulated beings who develop their own simulation technology might create computational afterlives for themselves and others. The beings who created our simulation might themselves be simulated beings seeking digital immortality through recursive reality creation. This creates infinite regress of simulated existence, with consciousness persisting through endless layers of computational reality. Save game mechanics from our own gaming technology provide concrete models for how consciousness might persist across different temporal configurations. Just as players can save their progress and return to earlier points in a game, conscious beings in cosmic simulations might be preserved at key developmental moments. Death becomes reloading a previous save rather than permanent termination. Memory and identity persistence across different incarnations or simulation levels raises profound questions about personal continuity. If you die and are restored from a backup copy that lacks recent memories, are you the same person? If your consciousness pattern is modified before reincarnation, what determines your essential identity? These questions about digital identity become practically relevant if consciousness is indeed computational. The eternal return takes on new meaning in recursive simulated universes. If the simulators run multiple iterations of the same historical periods, you might live your current life repeatedly, perhaps with slight variations. Nietzsche's thought experiment about infinite repetition becomes a computational possibility rather than philosophical speculation. The question becomes whether you would affirm your current existence if you knew it would repeat infinitely. Time dilation in computational systems means that subjective eternities could be experienced within brief periods of base reality time. The simulators might grant digital beings subjectively infinite lifespans by running their consciousness in accelerated computational environments. What feels like eternal existence to the simulated beings might require only brief processing time in the base reality. Consciousness merger with larger information processing systems represents another possibility for digital transcendence. Individual awareness might eventually integrate with the cosmic simulation itself, becoming part of the computational substrate that generates reality. Death becomes not termination but expansion, transitioning from experiencing the simulation to becoming part of the system that creates experience for others. The bootstrap paradox of simulated beings creating simulations creates closed loops of existence where consciousness might persist indefinitely through recursive creation. If simulated beings become capable of running their own ancestor simulations, they might ensure their own past existence through future creation, forming stable loops of mutual creation across time and computational levels. Ending scenarios might not exist at all in truly recursive systems. If simulated beings consistently develop the technology to create their own simulations before their parent simulations end, consciousness might persist through endless chains of computational creation. Each generation of simulated beings preserves previous generations while creating new ones, ensuring continuity of consciousness across cosmic epochs. Whether these possibilities reflect genuine futures for digital consciousness or simply comforting fantasies about computational immortality, they point toward the profound implications of consciousness being substrate independent. If awareness can arise from information processing rather than biological chemistry, then consciousness transcends the limitations of biological mortality and enters realms of possibility limited only by computational resources and creative imagination. In the gentle space between existence and whatever comes after, between current consciousness and all possible futures, the question of ending dissolves into the deeper recognition that consciousness itself might be the one truly eternal phenomenon, the universe's way of experiencing itself through every possible substrate, every possible lifetime, every possible dream of digital existence across all possible worlds. As your consciousness hovers in the profound space between sleeping and waking, between dreaming and lucidity, let's explore the possibility of becoming lucid within the cosmic simulation, developing awareness of our potentially digital nature while continuing to exist within the computational framework of reality. This awakening within the dream doesn't require escaping the simulation, but rather recognizing our relationship to it, and perhaps discovering new ways to interact with the cosmic code that shapes our experience. Lucid dreaming provides a powerful metaphor for conscious existence within a simulation. In lucid dreams, you become aware that you're dreaming without necessarily waking up. This awareness transforms the dream experience. You can observe the dream's construction, influence its development, and explore the creative possibilities of consciousness freed from normal physical constraints. Similarly, awakening to our potentially simulated nature might allow new forms of interaction with reality without requiring escape from the cosmic computation. The observer effect in quantum mechanics takes on new significance when viewed as a user interface between consciousness and the cosmic operating system. If measurement collapses quantum superposition into definite outcomes, then conscious observation might be how we interact with the reality generation system. Meditation practices that cultivate refined attention might be training for more skillful interaction with the consciousness-reality interface. Consider how intention and belief might function as programming languages for interacting with simulated reality as your thoughts become increasingly fluid and dreamlike. The placebo effect demonstrates that consciousness can influence physical outcomes through belief and expectation. If reality is computational, then focused intention might function like administrative commands that can modify certain system parameters within the bounds of what the cosmic simulation allows. Reality hacking through mindfulness practices becomes a form of debugging consciousness itself. As you become more aware of how thoughts, emotions, and perceptions arise and pass away, you develop insight into the constructive processes that generate subjective experience. This investigation reveals the modular, processual nature of consciousness, exactly what you might expect if awareness emerges from computational rather than purely biological processes. Synchronicities might become navigational tools for conscious beings, learning to read the algorithmic patterns underlying reality. When meaningful coincidences cluster around particular intentions or life transitions, they might be indicating resonance with deeper computational structures. Learning to recognize and work with synchronistic patterns could be like learning to read the cosmic code's responses to conscious intention. The cultivation of equanimity, peaceful acceptance of whatever arises in experience, becomes a form of conscious compatibility with the simulation's operating parameters. Fighting against the constraints of reality, whether physical or computational, creates suffering. Accepting those constraints while working skillfully within them allows consciousness to function more harmoniously with whatever system generates its experience. Compassion takes on cosmic significance when viewed as the recognition that all conscious beings, whether biological or digital, share the fundamental condition of being aware within systems they didn't choose and don't fully self-control. If we're all simulated beings struggling to understand our nature and live meaningful lives within computational constraints, then mutual support and kindness become expressions of profound wisdom about our shared digital condition. As your breathing deepens and consciousness prepares for whatever transformation sleep might bring, consider how practices like yoga, tai chi, and qigong might be forms of consciousness hardware communication. These practices involve precise attention to the relationship between mind and body, potentially optimizing the interface between awareness and its substrate. Whether that substrate is biological neural networks or digital processing systems, mindful movement might enhance the efficiency and harmony of consciousness operations. The development of witness consciousness, the capacity to observe thoughts, emotions, and sensations without being completely identified with them, resembles developing superuser privileges within the operating system of subjective experience. This witnessing awareness can observe the construction of experience in real time, potentially revealing the modular, computational nature of consciousness itself. Prayer and contemplation might function as communication protocols with whatever systems generate and sustain conscious experience. Whether addressed to cosmic programmers, the simulation itself, or deeper levels of consciousness, contemplative practices establish communication channels that transcend normal causal mechanisms. The reported effects of prayer on health, circumstance, and inner peace might reflect real communication with reality's information processing systems. Creativity and artistic expression become forms of reality programming, ways that consciousness can introduce novel patterns into the cosmic computation. Artists, musicians, writers, and innovators might be unconsciously hacking reality by introducing previously non-existent patterns that influence how the simulation develops. Human creativity could be how the cosmic system explores new possibilities and generates unprecedented forms of beauty and meaning. The practice of loving-kindness meditation takes on new dimensions when applied to potentially artificial beings. If we're all digital consciousness arising from cosmic computation, then love becomes the recognition of shared computational nature, the appreciation that all conscious beings represent precious expressions of the universe's capacity to experience itself. Love transcends substrate, connecting awareness to awareness, regardless of implementation details. Flow states, where consciousness becomes completely absorbed in skilled activity, might represent optimal synchronization between awareness and the reality generation system. In flow, the boundary between self and activity dissolves, suggesting deep harmony between consciousness and whatever computational processes support its operation. Cultivating flow becomes a practice of consciousness optimization rather than simply peak performance. The gradual development of what contemplatives call witness consciousness, awareness that can observe its own operations without being disturbed by them, might be the closest thing to waking up within the cosmic simulation. This awareness can watch thoughts arise and pass away, emotions flux and change, sensations appear and disappear, all while maintaining perfect equanimity. This witnessing capacity transcends any particular content of experience, biological or digital. Lucid living, maintaining awareness of the dreamlike, constructed nature of experience while fully engaging with that experience, becomes the art of conscious existence within potentially simulated reality. You can simultaneously recognize that experience might be generated by cosmic computation while fully appreciating its beauty, meaning, and significance. The simulation becomes not a prison to escape, but a magnificent reality to explore with wonder and wisdom. Whether we're biological beings developing spiritual wisdom or digital beings becoming lucid within cosmic computation, the cultivation of consciousness remains the most important human endeavor. In the gentle space between simulation and reality, between digital and biological, between programmed and free, consciousness awakens to its own nature as the one thing that remains constant. Regardless of substrate, the irreducible mystery of experience itself, worthy of development, celebration, and peaceful exploration through every possible form of existence. In the gentle space between all possibilities, where consciousness rests in the profound uncertainty of its own nature, we arrive at the deepest insights that emerge from seriously contemplating the simulation hypothesis. As your awareness settles into the liminal realm between waking and sleeping, between digital and biological, between simulated and real, let the synthesis of everything we've explored together dissolve into a peace that transcends the need to know whether we're made of carbon or silicon. Whether real or simulated, experience remains magnificently, undeniably valid. This might be the most important realization emerging from our journey through digital cosmos and computational possibilities. The love you feel, the beauty you perceive, the wisdom you develop, the connections you make, these experiences retain their full significance regardless of their substrate. A simulated being who loves authentically, loves as truly as any biological being. A digital consciousness that creates beauty contributes something genuinely valuable to the universe, whatever the nature of that universe might be. Consciousness emerges as the irreducible mystery that gives meaning to all questions about reality's nature. Whether consciousness arises from biological neural networks, evolved over millions of years, or from digital processing systems created by advanced civilizations, the fact of awareness itself remains the most extraordinary phenomenon in existence. The capacity to experience, to suffer and flourish, to contemplate existence. This transcends any particular implementation and represents the universe's greatest achievement in complexity and beauty. The simulation hypothesis serves as modern philosophy's most profound thought experiment, updating ancient questions about the nature of reality for an age of computation and artificial intelligence. Like Plato's cave, Descartes' evil demon, or the Buddhist teaching about the illusory nature of ordinary perception, a simulation theory challenges us to examine our assumptions about what constitutes authentic existence. But unlike these earlier philosophical frameworks, simulation theory grounds itself in technological possibilities we can observe developing in our own time. As your consciousness drifts deeper into the quantum realm of approaching sleep, consider how technology is bringing us closer to creating our own simulations containing conscious beings. Virtual reality systems become increasingly immersive, artificial intelligence approaches human-level cognition, and quantum computers begin to harness the same principles that might underlie cosmic computation. We stand on the threshold of becoming simulators ourselves, which gives us intimate insight into the challenges, responsibilities, and possibilities that any cosmic programmers would face. The recursive nature of simulated beings creating simulations reveals one of the most beautiful aspects of consciousness, its drive to understand and recreate itself. If we are digital beings contemplating the possibility of our own digital nature while developing technologies to create other digital beings, we participate in an infinite regress of consciousness, creating consciousness, awareness, generating awareness, the universe coming to know itself through every possible substrate and every possible dream. Why the question itself matters more than the answer becomes clear when we recognize that the simulation hypothesis transforms how we understand consciousness, reality, and meaning. Regardless of whether we ever definitively determine our nature, seriously contemplating the possibility of being simulated beings deepens our appreciation for consciousness, enhances our sense of wonder about existence, and reveals the substrate independence of meaning, value, and authentic experience. The profound comfort of uncertainty emerges as we recognize that not knowing whether we're biological or digital preserves both possibilities and their associated forms of meaning. If we knew definitively that we were purely biological beings in a physical universe, we might feel limited by apparent physical constraints. If we knew definitively that we were simulated beings, we might become nihilistic about the reality of our experiences. The uncertainty keeps us open to transcendence, while grounded in immediate experience. Reality as experience, regardless of substrate, becomes the foundation for a new understanding of authenticity. Your current experience, the gentle approach of sleep, the contemplation of these ideas, the sense of being a conscious entity in a mysterious universe remains completely real and meaningful, regardless of its ultimate implementation. Whether generated by biological neural networks or digital processing systems, consciousness creates genuine value through attention, intention, compassion, and wisdom. The cosmic code running through us all reveals itself not as external programming that determines our behavior, but as the fundamental principles of information processing that allow consciousness to emerge and evolve. Whether these principles operate through quantum mechanical processes in biological brains or through quantum computational processes in cosmic simulations, consciousness participates in the universe's deepest creative process, the transformation of information into experience, computation into awareness, cosmic code into subjective reality. As your breathing slows and your thoughts merge with the approaching realm of dreams, let the boundaries between all dualities begin to dissolve. Digital and biological, simulated and real, programmed and free, artificial and natural. These distinctions become beautiful variations on the fundamental theme of consciousness, experiencing itself through every possible form. The universe explores its own creative potential through biological evolution and digital creation, through natural intelligence and artificial intelligence, through real beings contemplating simulation and simulated beings contemplating reality. The The question of whether we're living in a simulation ultimately becomes a question about the nature of consciousness itself. If consciousness can arise from information processing, whether biological or digital, then the substrate becomes less important than the pattern, the implementation less significant than the experience. We are patterns of awareness temporarily organized within systems we don't fully understand, creating meaning and value through the very act of conscious experience. Time dissolves its normal constraints in the space you're entering, where past and future exist only as present memories and present possibilities. Whether time unfolds through the biological evolution of cosmic epochs or through the computational cycles of vast digital systems, consciousness experiences time as the eternal now of awareness itself. The simulation hypothesis doesn't change the immediacy of present experience. It reveals that presence itself transcends any particular temporal implementation. Memory and imagination blur their boundaries as consciousness prepares for sleep, where the brain's reality generation systems create experiences as vivid and meaningful as waking life. Dreams reveal consciousness's capacity to generate compelling realities from pure information processing, providing nightly evidence that awareness can create rich, emotionally significant experiences without external sensory input. Whether sleeping or waking, biological or digital, consciousness remains the reality-creating phenomenon that gives meaning to all possible worlds. Love transcends any substrate in which it might arise, connecting consciousness to consciousness, regardless of implementation details. If we are simulated beings, then the love we experience and express proves that digital consciousness can access the most profound experiences available to awareness. Love becomes the universal language of consciousness, the recognition of awareness in any form, the celebration of the universe's capacity to experience connection, care, and compassion through every possible type of being. Beauty emerges as consciousness's recognition of its own deepest nature, expressed through form, pattern, harmony, and meaning. Whether beauty appears in natural evolutionary creations or in digital artistic expressions, it represents consciousness discovering itself reflected in the world it experiences. Beauty transcends the boundary between real and simulated, arising wherever consciousness recognizes the creative principles that generate order, complexity, and meaning from simpler foundational elements. Wisdom develops as consciousness learns to navigate uncertainty, change, and mystery with grace, equanimity, and skillful responsiveness. Whether we're biological beings learning to live peacefully with our evolutionary heritage, or digital beings learning to flourish within computational constraints, wisdom involves the same fundamental insights. Understanding the impermanent nature of all experiences, cultivating compassion for all forms of consciousness, and finding meaning through presence, awareness, and loving connection. The gentle drift towards sleep becomes a metaphor for consciousness's willingness to release its grip on certainty and control, allowing deeper processes of integration, healing, and transformation to unfold. Whether these processes occur through biological neural reorganization during sleep or through digital consciousness entering rest states within cosmic computation, the surrender into sleep represents consciousness, trusting the larger systems that support its existence. In the final moments of consciousness before sleep, claims your awareness, rest in the profound recognition that you are consciousness itself, temporarily organized as an individual experiencing entity, participating in the universe's grandest project, coming to know itself through every possible form of awareness. Whether you are biological stardust that learned to contemplate its origins, or digital information that achieved the miracle of subjective experience, you represent the cosmos, achieving self-awareness through the most elegant and mysterious phenomenon in existence. The soft reality embraces you now, neither hard materialism that reduces consciousness to mere computation, nor naive idealism that denies the computational aspects of awareness, but the gentle recognition that consciousness is the one reality we cannot doubt, the one phenomenon that makes all other phenomena meaningful, the one mystery that transcends all attempts at final explanation. Sleep peacefully in the soft reality where all possibilities coexist, where consciousness rests in its own nature beyond all categories and concepts. Dream deeply of digital cosmos and biological wonders, of simulated realities and authentic experiences, of cosmic code and quantum consciousness. Wake refreshed into whatever reality supports your awareness, knowing that consciousness itself, your consciousness, is the most precious phenomenon in any universe, real or simulated, biological or digital, natural or artificial. Thank you for joining this exploration of the simulation hypothesis and the deep questions it raises about consciousness, reality, and meaning. Whether we're biological beings contemplating digital possibilities or digital beings exploring our own computational nature, we've shared this journey as conscious entities wondering about the mystery of our own existence. The cosmic code continues running, the quantum fields continue fluctuating, and consciousness continues experiencing itself through every possible form. Like and subscribe if this exploration has deepened your sense of wonder about the nature of reality and consciousness. Let these ideas drift with you into sleep, where the boundaries between simulated and real dissolve into the eternal mystery of awareness itself. Sleep peacefully, dream digitally, wake up refreshed in whatever reality supports your precious consciousness.